On the night of November 14th, 2023, the oldest working machine our species has ever sent anywhere called home right on schedule. The call came from 15 billion miles away. Voyager 1, launched in 1977, had been flying for 46 years, and in all that time, it had never once missed an appointment. The giant dish antennas in the California desert locked on, and there it was, the familiar carrier tone. Steady as a heartbeat, the spacecraft was alive. Its power was on. Its antenna was pointed at Earth with the patience of half a century. Then the engineers looked at what it was actually saying, and the room went quiet. The message was garbage. One meaningless pattern of ones and zeros, repeating over and over, like a needle stuck in a groove. Imagine sitting with someone you love after a stroke. The eyes are open, the lips are moving, and the words coming out are sounds with no language left inside them. That was Voyager 1 that November night, the farthest thing humanity has ever touched. Talking in its sleep across 15 billion miles. Here is what should scare you. And here is why this video exists. Whatever broke that spacecraft was not a rock. Nothing hit it. There was no explosion, no storm, no dramatic last stand. Something far smaller than that happened out there in the dark. Something that has been quietly stalking every machine we have ever launched. And to understand what it was, you have to understand every way a spacecraft can die. So tonight we ask the question straight. How long can our spacecraft actually survive in space? The answer will not be one number. A spacecraft does not carry one lifespan. It carries dozens of countdown clocks, all ticking at once, at different speeds, and a mission ends the moment the very first clock reaches zero. Tonight we walk through every one of those clocks, and we find out which ones tick fastest. And I owe you a promise before we start. At the end of this video, I will hand you the real number. The full lifespan of these machines after the last person stops listening. The number does not come in decades. It does not come in centuries. It is so much larger than that. So genuinely absurd that NASA once hired a man to draw a map of what Earth will look like in the far future, just so they could bolt that map onto one of these machines before it left. Keep watching and you will see that map. If you love this kind of deep dive into space as much as we do, take a second to like this video and subscribe. It genuinely helps the channel reach more curious minds like yours. Now, back to Pasadena. The room where Voyager lives is nothing like the movies. Forget mission control from the Apollo films. The stadium of consoles. The wall of screens. The 100 headsets. The Voyager flight team works out of ordinary offices at the Jet Propulsion Laboratory in Pasadena, California, and on most days that team is about a dozen people. Some of them are younger than the spacecraft they are keeping alive. The mission has outlived careers, outlived retirements, outlived several of the engineers who designed it. The people fixing Voyager today are, in a very real sense, doctors treating a patient born before they were. And treating this patient comes with a rule that no doctor on Earth has ever faced. The patient is 15 billion miles away, and even at the speed of light, a question takes 22.5 hours to get there. The answer takes another 22.5 hours to come back. Ask the spacecraft how it feels on Monday morning, and you hear back Wednesday morning. Every exchange, every test, every guess costs you nearly 2 full days. And there are no second opinions, no house calls, and no spare parts. Nobody has ever repaired anything at that address. Nobody ever will. Now add the age of the machine itself. The computers on Voyager 1 were designed in the early 1970s. All of its memory combined is smaller than a single photo on your phone. Smaller than the software inside the key fob that unlocks your car. The engineers who wrote its code wrote it in languages most programmers alive today have never used. For hardware that exists nowhere on Earth except in filing cabinets and museum cases. When something breaks out there, the team pulls schematics printed when Nixon was president and reads the handwriting of men who have been gone for decades. That November night, the team started a diagnosis that would take months, and I'm going to leave them there for now, working the problem, because we will come back to this room more than once tonight. What they eventually found, the actual culprit, is waiting for you in Chapter 7. And when we get there, you will understand why it is one of the most unsettling failure stories in the history of spaceflight. But we cannot get there yet, because the question this video asks has a trap hidden inside it, and we need to spring that trap first. I asked how long a spacecraft can survive. Before anyone can answer that, we have to agree on something that sounds obvious and absolutely is not. What does it even mean for a spacecraft to be alive? Somewhere in America right now, there is a car sitting in a garage that has not started in 10 years. Maybe you know the car I mean. Maybe it belonged to your grandfather. The tyres are soft. There is dust on the windshield thick enough to write in. And the battery died sometime during a winter nobody remembers. So answer me this. Is that car dead? Because here is the strange part. The engine is fine. The transmission is fine. Every gear and valve and piston is sitting exactly where the factory put it. Charge the battery. Pour in fresh gas. Turn the key. And there is a very good chance that car clears its throat and runs. So for 10 years, what was it? It was not working. But it also was not gone. It was somewhere in between. In a grey zone, our everyday language does not have good words for. Spacecraft live and die in that grey zone. And if we are going to spend tonight asking how long they survive, we need better words than alive and dead. So let me give you the scorecard we will use for the rest of this video. There are 5 levels of survival for any machine we send into space. And I want you to actually keep count as we go, because every spacecraft you meet tonight is going to land on a different rung of this ladder. Level 1. The spacecraft still exists. The physical body, the metal and glass and wiring, is still in one piece, still out there, still holding its shape against the dark. Level 2. The spacecraft has power, somewhere inside it. Electricity is still flowing. The heart is still beating. Level 3. The spacecraft can control itself. It knows which way it is facing, and it can do something about it. It can hold its antenna toward Earth, hold its solar panels toward the sun, point where it needs to point. This one sounds boring, and it is anything but, because you are going to watch healthy spacecraft die tonight for losing this and this alone. Level 4. The spacecraft can communicate. Earth can still hear it, and it can still hear Earth. Level 5. The spacecraft can do science. It can still take the pictures, run the instruments, gather the data it was born to gather. This is the reason it exists. And it is always, always the first thing to go. Now, here is the rule that makes tonight interesting. These 5 levels do not fail in order. They collapse in the strangest sequences, and the sequence tells you everything about what killed the machine. Let me show you what I mean with 3 quick teasers. 3 spacecraft we are going to meet properly later tonight. There is a space telescope that lost level 3, lost the physical ability to hold itself still, which for a telescope is death. Plain and simple. Its mission was declared over, and then its engineers found a replacement part, something to lean against. Except the replacement part was not on the spacecraft. It was 93 million miles away, and it worked. That rescue is Chapter 12, and it is one of the cleverest things human beings have ever done. There is another spacecraft, orbiting a dwarf planet right now, that died with almost a perfect scorecard. Power, fine. Computers, fine. Instruments, fine. It failed at exactly one thing, and that single failure took everything else down with it in a matter of days. That story is Chapter 11, and it is the purest example you will ever see of how these machines actually die. And there is a little aluminum sphere, about the size of a grapefruit, that America launched in 1958, its batteries died in 1964, which means it has been silent for over 60 years. Level 2, gone. Level 4, gone. Levels 3 and 5, gone. By every casual definition, that thing is dead. But run it through our scorecard, and level 1 is untouched. And level 1 is going to stay untouched for a very, very long time. That little sphere is passing over your head tonight. And it will still be passing over the heads of Americans who have not been born yet. In a century that has not started yet, it is the oldest human object in space. And near the end of tonight, it is going to force us to rewrite the question this whole video is asking. So hold the scorecard. 5 levels. Existence. Power. Control. Communication. Science. A spacecraft can be dead at the top and alive at the bottom. Dead in the middle and alive at both ends. And from here on out, every time a machine dies tonight, we are going to run the numbers and find out exactly which level failed first. Which raises the next question. The obvious one. Who decides how long those levels are supposed to last? Because every spacecraft that leaves this planet has a lifespan written down on paper before it ever feels a launch pad. A number typed into a document years before liftoff. And the gap between that written number and the truth is one of the strangest running jokes in the entire space program. NASA once landed a rover on Mars with a warranty of 90 days. I want to tell you what happened to it. Because the story of that rover is the story of every clock we are about to meet. And it starts with an engineering promise that sounds, at first, like a lie. One number on paper. 90 days. Chapter 3 is about what that number actually meant, and why the rover it belonged to refused to honour it. Go find the paperwork from the last washing machine you bought. Somewhere in that folder is a warranty, and that warranty says something like 3 years. Parts and labour. Now ask yourself what that number actually means. It does not mean the machine self-destructs on the first morning of year 4. Nobody at the factory installed a 3-year fuse. What that number really says is this. We, the manufacturer, are willing to sign our name to 3 years. We have tested this thing. We know how it fails. And we are confident enough to bet money on 3 years. Privately, the engineers who built it expect it to run for 10 or 15. The warranty is not a prediction. It is a promise with a signature under it. Every spacecraft that has ever left this planet carries a number exactly like that. And it is one of the most misunderstood numbers in all of spaceflight. Engineers call it design life. The press calls it the mission length. And when a spacecraft blows past that number by years or decades, headlines treat it like a miracle, like the machine somehow cheated death. It did not cheat anything. It was simply doing what warranties do. Here is how the number gets made. And I promise this is stranger than it sounds. When NASA designs a mission, it does not ask, how long can this spacecraft last? It asks a colder question. What is the shortest lifespan we can guarantee? At a confidence level, we would stake careers on every component on board, every circuit board, every hinge, every valve, gets tested and rated and assigned its own odds of surviving. Then, all those odds get multiplied together into one final probability, and that probability has to clear a very high bar for the length of the primary mission. If the math says we are barely confident at 5 years, the design life is 5 years, even if the same math whispers that the hardware will probably run for 20, and that little word probably is doing enormous work. Because to make the guarantee stick, engineers do something that would look insane in any normal industry. They build the spacecraft twice. Not 2 spacecraft. 1 spacecraft, with 2 of nearly everything inside it. 2 flight computers, 2 radio transmitters, backup thrusters, backup heaters, backup sensors. Engineers call it redundancy. and it means a spacecraft is really a body carrying a second set of vital organs, sealed and silent, waiting for the first set to fail. Later tonight, you will watch a backup system get woken up after 21 years of sleep, and you will find out what that feels like for the people sending the wake-up call. But redundancy has a limit, and the limit has a name that shows up in every risk report ever written. Single point failure. Some parts of a spacecraft exist exactly once, because there was no room, no weight allowance, or no way to double them. One main antenna dish, one fuel tank, one hinge on one critical panel. Every one of those is a place where a single bad day kills the entire mission, no matter how healthy everything else is. And engineers keep lists of these points the way heart surgeons keep lists of arteries. So that is the machinery behind the number. Now let me show you the most famous gap between the number and the truth in the history of exploration. In the summer of 2003, NASA launched a rover called Opportunity toward Mars, and the design life written into that mission was 90 days. 90 Martian days on the surface, which comes out to about 3 Earth months. That number was not modesty, and it was not a lowball to make the team look good later. It came from a real, physical, countdown clock, and the clock was made of dust. Opportunity ran on solar panels, and Mars is a dusty world. There is no rain there to rinse anything clean, and the engineers knew, from previous missions, roughly how fast the fine red dust settles out of the Martian sky onto every flat surface. They ran the numbers on that falling dust, layer by layer, week by week, and the numbers said that around day 90, the panels would be wearing a blanket thick enough that the rover could no longer charge its batteries through it. This was arithmetic. Dust falls at a known rate. Power dies on a known schedule. You could write the rover's obituary before it launched. And in a very real sense, they did. 90 days of guaranteed science. And then a slow brownout on a cold red plain. Everyone signed off on it. The rover launched with its funeral already penciled on the calendar. Opportunity landed in January of 2004. Bounced across the plains of Meridiani inside a cocoon of airbags. Rolled out. Unfolded its panels. And went to work. The dust began falling on it that first day. Exactly as predicted. And the power readings began their slow decline. Exactly as predicted. Day 30. Day 60. The math was holding. The blanket was building. Day 90 came. The warranty expired. And the rover kept driving. Its power was lower. Its panels were dimming under the falling dust. And by every projection in every planning document, it was living on borrowed time. Days from a quiet death. Then the engineers in Pasadena noticed something in the power data that nobody had dared put in a plan. Something had happened to those solar panels overnight. Something that was not in the dust arithmetic. And the power readings were doing the one thing they were never supposed to do. I am going to stop right there. And I know exactly what I am doing by stopping. What happened to that rover? What kept happening to it? And the storm that finally ended everything, 15 years later. All of that is Chapter 9. And I want you to have the full picture of what Mars throws at a machine before I hand you the ending. What matters tonight, at this point in our story, is the principle. 90 days was never a lifespan. It was a floor. And the distance between the floor and the ceiling turned out to be one of the great engineering stories of our time. Here is the thing. Though, every spacecraft that gets to have a floor at all, every machine that gets the chance to outlive its paperwork, has already survived something that the paperwork barely covers. Before the dust, before the radiation, before any of the slow patient killers we are going to spend tonight with, there is a single day that stands apart from all the rest. The most dangerous day in the life of any spacecraft is its first one, because a machine built to whisper across billions of miles for 50 years has to begin its life strapped to the top of a controlled explosion. Picture a grand piano, handmade, wildly expensive, tuned to perfection over months by people who love it. Now strap that piano to the top of a 20-story building filled with explosives. Light the bottom of the building on fire, and shake the whole thing like a paint mixer for 8.5 minutes. When the shaking stops, the piano has to play a flawless concert. Its first one. From orbit, that is a rocket launch. From the spacecraft's point of view, and the numbers behind it are worth feeling. A machine assembled by technicians in bunny suits. In a clean room where a single human hair on the floor triggers paperwork. Where components are handled like organ transplants. Gets bolted to the nose of a vehicle that is, by design, a barely tamed bomb. Roughly 95% of a rocket sitting on the pad is fuel. The payload, the actual reason for the whole event, that priceless machine up top, is a rounding error riding a firestorm, and the violence comes in 3 distinct flavors, one after another, each with its own way of killing. The first flavor is shaking. From the moment the engines light, the entire vehicle vibrates like a struck bell that refuses to stop ringing. Every solder joint on every circuit board, every bolt, every bracket, every wire tie inside the spacecraft gets rattled thousands of times per minute. And here is what makes engineers lose sleep. Every object has frequencies it naturally likes to swing at. The way a wine glass has a note that shatters it. If any part of the spacecraft resonates with the rocket beneath it, the shaking amplifies itself, and things that survived every test on Earth can crack in seconds. So years before launch, the whole spacecraft gets strapped to giant shake tables in a lab and rattled mercilessly, on purpose, while engineers hunt for the one bracket, the one panel, the one instrument mount that sings along. The second flavor is sound, and this one surprises people, because it sounds almost gentle. It is anything but. A heavy rocket at full thrust is among the loudest things human beings have ever created. And I do not mean loud like a concert. I mean sound as a physical weapon. Pressure waves violent enough to damage hardware. At ignition, that roar slams down into the concrete flame trench, bounces, and comes right back up at the vehicle like an echo with fists. The sound alone, reflected off the ground, can crack solar panels and tear at antennas before the rocket has climbed its own length. This is why launch pads drown themselves at ignition. If you have ever watched a launch and seen those towers dump a flood onto the pad, hundreds of thousands of gallons in under a minute, that water is not primarily fighting fire. It is there to soak up sound, to smother the echo. A swimming pool sacrificed in seconds so that the machine on top does not get beaten to death by its own voice. The third flavor is the punch list. Rockets are built in stages, and every stage that finishes its job gets thrown away in flight. Explosive bolts fire. The spent stage falls away. The next stage lights. Each separation is a bang and a jolt travelling through the spacecraft's bones. A series of short, sharp shocks in the middle of the ride, any one of which can pop a connector loose or jar a mechanism 0.5 millimeter out of place, which in this business can be the whole ballgame. 8.5 minutes after leaving the pad, more or less, the shaking stops, the noise is gone, and the spacecraft is in space, floating in a silence more complete than any it will ever have known on Earth. And you would think that is the moment everybody in mission control exhales. It is not, because now comes the part of the first day that has quietly killed more missions than the fire and the noise ever did. Now the spacecraft has to unfold, to fit inside the rocket's nose cone. Almost everything on a spacecraft launch is folded. The solar panels pinned flat against the body, the antennas stowed and latched. Booms and covers and radiators all tucked in like a moth inside a cocoon. Every one of those parts now has to swing out, lock into place, and hold, driven by hinges and springs and little motors that have exactly one job. On exactly one day, with exactly 0 second chances, there is no undo. There is no reaching over to jiggle the latch. A communications satellite whose solar panels fail to open is a corpse with a warm battery, tumbling in full view of the ground stations that can hear it perfectly and cannot help it at all. It happens. It has happened enough times that the industry has a grim respect for it. Missions worth hundreds of millions of dollars. Years of work by thousands of people. Ended not by an explosion but by one hinge that did not finish its swing. Run that through last chapter's scorecard and feel how strange it is. A satellite like that still exists. Level 1. Intact. It still has power. Level 2. Beating heart. And it is already dead. Because Level 3. Control. Or Level 5. Purpose. Died in the fold. The autopsy takes 10 seconds. The funeral takes years of insurance lawyers. If you want to know how seriously the people in this business take deployment, look at what happened on Christmas morning of 2021. When NASA launched the James Webb Space Telescope, the most expensive science machine ever sent off this planet. Webb was too big for any rocket in existence. A mirror wider than the nose cone meant to carry it. A sunshield the size of a tennis court. So the whole observatory launched folded like origami. And over the 2 weeks after liftoff, it had to open itself. Step by step, joint by joint. 1,000,000 miles from any possible help, the engineers counted the steps that had no backup. The single-point failures we met last chapter. The moments where one stuck pin or one torn membrane ends the entire $10 billion project. On Webb's deployment, the count came to 344. 344 separate mechanisms and events. Every single one mandatory. Every single one unrepairable. Lined up in a row like dominoes that must not fall. The team called that stretch 2 weeks of terror. And they meant it. And for 14 days, the whole field held its breath, while a machine 1,000,000 miles away performed surgery on itself. All 344 worked. Every pin, every latch, every motor. Webb unfolded perfectly. And somewhere in that fact is the quiet answer to why spacecraft cost what they cost. You are not paying for the metal. You are paying for 344 yeses in a row. So the spacecraft survives the fire, survives its own voice, survives the punches, and unfolds without a single stuck hinge. The launch team claps, hugs, goes home, and sleeps for a day. On the drive home, every one of them believes the same thing. And you would believe it too. The hard part is over. The machine made it through the storm. And now it gets the easy part. The long, quiet cruise through nothing. And for the first few days, space cooperates with that belief. No weather out there. No rain. No rust. No gravity dragging on the joints. The spacecraft coasts through a stillness that looks, from the inside, like the safest place a machine has ever been. It took our species years of hard lessons to understand what is actually wrong with that picture. The nothing is not empty. The nothing has teeth. And in the first hours of the mission, before the crew back on Earth has even slept off the launch party, the nothing has already started chewing. Set a glass of water on a table, walk away, and imagine we could switch off the air in the room. The water does not sit there. Within seconds, it boils. No stove, no flame, no heat at all. The glass just erupts into a rolling, violent boil at room temperature, because the only thing that was ever holding that water together as a liquid was the weight of the atmosphere pressing down on it. Take the air away, and water simply cannot remain water. It tears itself apart into vapour. Now understand that everything is a little bit like that water. Every material on Earth, every plastic, every paint, every glue, holds a faint haze of trapped gas and moisture inside it, kept in place by the pressure of the air we live in. The moment you carry a machine above the atmosphere, all of it starts to leave. Engineers call it outgassing, and it begins within hours of launch. The spacecraft that survived the fire and the shaking now starts. Very quietly, to exhale. Its circuit boards exhale. Its insulation exhales. Its adhesives. Its wire coatings. Its paint. All of it breathes out a thin, invisible fog of molecules. And if that fog simply drifted away into space, this would be a piece of trivia and nothing more. It does not drift away. It lands. Here is the cruel physics of it. A molecule that leaves a warm surface floats until it touches a cold one. And then it sticks. The exact same way your breath fogs the inside of your windshield on a January morning. The breath leaves your warm body, hits the coldest glass in the car, and condenses. Now ask yourself, what are the coldest surfaces on a space telescope? The detectors, the mirrors, the lenses, the precision optics that are deliberately chilled to make them sensitive, the most delicate and least replaceable surfaces on the entire machine, are also the coldest, which means the spacecraft's own breath settles preferentially onto its own eyes. This is not theory. The Cassini spacecraft, on its way to Saturn, developed a haze across its main camera, and the pictures coming back grew soft and smeared, as if the mission had cataracts. The culprit was contamination fogging the cold optics, and the fix sounds like something out of a folk remedy. Warm the camera up and hold it there. The team gently heated the instrument and kept it warm for weeks, evaporating the film off the glass molecule by molecule, and it worked. The eye cleared, but sit with the absurdity of the situation. A billion-dollar mission, halfway across the solar system, was partially blinded by its own exhaled breath, and the treatment was patience and a heater, and the exhaling is only the vacuum's first trick. The second one is meaner, because it goes after the joints. Every machine you have ever owned depends on lubrication, on thin films of oil and grease sitting quietly inside bearings and hinges, and all of it was formulated for a world with air pressure. In vacuum, ordinary oils do what the water in our glass did. They boil off, slowly, molecule by molecule, or they creep and migrate to places they were never meant to be. A hinge that swung freely on the launch pad can, years into a mission, find its grease simply gone, evaporated into the dark, and there is no mechanic and no grease gun within 100 million miles. Every moving part launched into vacuum is in a slow race between finishing its job and losing its oil. Which brings us to the third trick. And the third one sounds like science fiction. In vacuum, bare metal can weld itself to bare metal, spontaneously, with no heat, no spark, no warning. Here is why. Two pieces of metal touching each other on Earth are never actually touching. Every metal surface in our world wears a microscopically thin coat of oxide, a film of corrosion just atoms thick, created instantly by contact with oxygen, and that invisible film is the only thing keeping the two metals apart. Strip the film away, press two pieces of clean identical metal together in vacuum, and the atoms on each side genuinely cannot tell which part they belong to. There is no boundary. The two pieces begin to bond into one piece, a process called cold welding, and in the airless dark there is no oxygen to rebuild the film and stop it. On Earth, metal touching metal is a handshake. In space, given time and pressure and cleanliness, it can become a permanent grip. Now let me tell you about the antenna, because this is where all three of the vacuum's tricks converge into one of the most painful moments in the history of exploration. In 1989, NASA launched Galileo, a flagship mission to Jupiter, and the crown jewel of its design was the main antenna, a beautiful gold mesh dish 16 feet across, built to fold like an umbrella for launch. In April of 1991, with the spacecraft safely on its way, the command went up, "Open the umbrella." The motors hummed, the ribs began to swing out, and then the whole mechanism ground to a halt, because a few of the antenna's ribs were stuck to the central tower, and no amount of coaxing would free them. The best reconstruction goes like this. Galileo, before launch, spent years in storage and made multiple truck trips across the country, and all that time and vibration wore away the lubricant on tiny pins in the mechanism. Then in vacuum, bare pin pressed against bare socket, with nothing left between them, and the metal held the metal, and the umbrella never opened. Not that day. Not ever. The team tried for years. They hammered the mechanism with motor pulses. They turned the spacecraft to bake the tower in sunlight and then freeze it in shadow, hoping expansion and contraction would pop the pins loose. And the grip never gave. A mission designed to stream Jupiter home through a 16-foot dish had to whisper instead through a tiny backup antenna, at data rates thousands of times slower. A garden hose replaced by an eyedropper. The only reason Galileo is remembered as a triumph is that engineers on the ground spent years teaching a 1970s-era computer new compression tricks mid-flight, squeezing science through that eyedropper, one precious drop at a time. The mission was saved. The dish never opened. Somewhere out there, that gold umbrella burned up with the spacecraft still folded, held shut by a grip no human hand ever touched. And underneath all three of these tricks, the exhaling, the vanishing oil, the metal handshake, the vacuum holds one more truth, the deepest one, the one that shapes every spacecraft ever drawn. In vacuum, a machine cannot sweat. Every device you own is being rescued by air. Right now, constantly, the laptop on your desk, the phone in your pocket, the refrigerator in your kitchen, all of them shed their waste heat into moving air, and moving air carries it away. That process, convection, is the invisible janitor of our entire civilization, and above the atmosphere, it does not exist. There is no air to carry anything anywhere. A spacecraft generating heat, and every computer and every radio generates heat with every watt it uses, is a body wrapped in the most perfect blanket ever made. And the only way to shed warmth is to glow it away as radiation, the slowest cooling method in nature. This is why spacecraft wear those strange mirrored blankets, why they sprout dark panels that serve no purpose except to glow heat into the sky, why thermal engineers plan the journey of every single watt from the chip that makes it to the panel that finally spits it into space. Cooling, on Earth, is free. Out there, it is a plumbing system for warmth, designed part by part, and if any section of that plumbing fails, the spacecraft cooks itself with its own thoughts. So no, the nothing is not empty, and it is not gentle. It steals breath. It steals oil. It fuses joints. It wraps blankets. But the vacuum, for all its patience, is only the stage. The real torture of the first years of a spacecraft's life is the thing pouring across that stage. 8 light minutes from the sun, and switching off 16 times a day, because space is not cold. I know every movie has told you it is. The truth is stranger and much harder on machines. Space is cold and hot at the same time, in the same minute, on the same piece of metal, divided by a line thinner than a sheet of paper. And that line sweeps across every spacecraft like a blade on a schedule. There is an experiment you have already run, probably as a bored kid in a backyard somewhere, that explains why satellites wear out. Take a piece of wire, a coat hanger. Say, try to snap it with your hands and you cannot. The steel just laughs at you. But bend it, and straighten it, and bend it again. 10 times, 20. Somewhere around 30 bends, the wire stops fighting. The bend point goes soft and strange, and the steel comes apart in your fingers like taffy. You did not overpower that wire. Not once did you come close. You defeated it with repetition. Because metal keeps score. Every bend leaves invisible damage stacked on the damage before it. And when the score gets high enough, the strongest wire in the drawer simply quits. Engineers call it fatigue. And fatigue is the reason the killer in this chapter is not temperature. It is temperature change. On a schedule. Forever. Come up to low Earth orbit and ride one lap with a satellite. The lap takes about 90 minutes. And for roughly an hour of it, the satellite hangs in raw sunlight. No atmosphere to soften anything. The full unfiltered blast of the sun pouring onto its skin. The lit surfaces climb past 200 degrees Fahrenheit. Hotter than boiling water. Hot enough to cook with. Then the satellite's path carries it around the curve of the planet. And it crosses into Earth's shadow. And the sun does not set so much as vanish. Like a light switch thrown in an empty room. No air holds any warmth around it. The heat radiates away into blackness. And within minutes, the same metal that was oven hot is plunging toward 200 degrees below zero. Half an hour later, the satellite swings back around the curve of the world, and the sun slams on again. Oven, freezer, oven, freezer, 16 times every single day. Because the lap takes 90 minutes, and there are 16 laps in 24 hours. 16 times a day. Every material in that machine expands in the heat and shrinks in the cold. And here is where the trouble compounds. Because a satellite is not made of one material. It is aluminum bolted to titanium, glass bonded to plastic, copper wires soldered to boards. And every one of those materials swells and shrinks by a different amount. Aluminum stretches more than steel. Solder moves differently than the board it grips. So at every joint, every glue line, every bolted seam where two different materials meet, the two sides are constantly moving by different amounts, grinding against each other with each swing, like two hands ringing a tavel. 16 times a day. Every day. For years. Do the arithmetic on that, and the number should widen your eyes. 16 cycles a day is close to 6,000 cycles a year. A satellite on a 15-year mission takes nearly 90,000 trips between the oven and the freezer. Now think back to the coat hanger. 30 bends killed it. These machines are asked to survive 90,000. And mostly, astonishingly, they do. Because thermal engineers spend entire careers choosing materials that expand alike. Designing joints with slack in them. Wrapping the body in those gold and silver blankets, whose whole job is to flatten the swings. But nobody wins against fatigue. You only postpone it. Solder joints grow microscopic cracks that lengthen cycle by cycle. Bonded panels loosen their grip one swing at a time. Up on the International Space Station, which has been riding this 16-a-day rhythm for more than 25 years. Engineers now track small cracks in parts of the station's aging structure. The coat hanger score of a quarter century. And we will come back to that station and its scars in Chapter 8. So that is the everyday version of heat in space. The grinding, unglamorous version that wears out ordinary satellites in ordinary orbits. But this chapter has a second half. Because at this point, an obvious question should be forming. If a machine in Earth orbit, 93 million miles from the Sun, gets cooked past boiling on its sunny side, what happens to a machine that flies toward the fire? In August of 2018, NASA launched a spacecraft built to answer exactly that. And its destination sounds like a typo. The Parker Solar Probe was sent to fly into the Sun's outer atmosphere. Not toward the Sun, not near the Sun, into the halo of plasma around it. Again and again, diving closer with every orbit. Through territory where the environment does not merely warm a spacecraft but erases one. The temperature on Parker's sunward face, at closest approach, reaches about 2,500 degrees Fahrenheit. I want to anchor that number to something real. Lava, pouring out of a Hawaiian volcano, glowing orange and setting forests on fire. Runs cooler than that. The front of this spacecraft endures conditions hotter than flowing lava. And it does so repeatedly. on a schedule, as routine operations, and here is the number that makes Parker one of the proudest objects our species has built. While the front face stands in that furnace, the scientific instruments ride just behind it at about 85 degrees Fahrenheit. 85 degrees. That is a July evening in Georgia. That is shorts and a lawn chair and fireflies. The distance between lava and a summer evening on this machine is a heat shield about 4.5 inches thick, a sandwich of carbon foam faced with carbon plate, whiter than bone on its sun side to throw the light back. 4.5 inches. On one side of it, a furnace that would unmake the spacecraft in moments. On the other side, whether you would grill burgers in, but the shield is only half the miracle, and the other half is the part I need you to carry forward into the rest of tonight. Because it connects straight back to our scorecard. That shield only works if it stays exactly between the sun and everything else. Parker's instruments and antennas and radiators live in the shadow. In a cone of survivable shade, the shield casts behind itself, and the edge of that shade is a hard border. If the spacecraft's aim drifts, if the wrong face rotates even slightly into the light at closest approach, parts start dying in less time than it takes to describe the problem, and Parker faces this test alone. At closest approach, it is so deep in the sun's neighbourhood, moving so fast, that no warning from Earth could possibly arrive in time. Light itself needs 8 minutes to make the trip, so the spacecraft holds its own life in its own hands, ringed with sensors along the shield's edge that scream the moment sunlight touches anything it should not, wired to systems that twist the vehicle back into line within seconds. Automatically, with no human anywhere in the conversation. Remember level 3. Control. The boring-sounding level. The one about knowing which way you are facing. Parker Solar Probe is what level 3 looks like when it is the entire mission. This machine does not survive the sun by being tough. Toughness would buy it minutes. It survives by aim. By never once, in years of flying, letting the wrong side face the fire. The most heat-blasted object humanity has ever flown is, at its core, a machine whose real superpower is holding a pose. So a spacecraft can be built to stand in front of a furnace. It can be blanketed against the oven and the freezer, jointed against the grind, designed to outlast 90,000 swings, against everything this chapter threw at it. Engineering has an answer, because heat, for all its violence, plays fair. It comes from a direction. You can point a shield at it. The next killer does not come from a direction. It comes from every direction at once. It passes through the shield and the hull and the blankets, as if none of them were there. And it is not interested in the spacecraft's body. It is aimed, with terrible precision, at the spacecraft's mind. You have already seen its work. It is the reason a machine, 15 billion miles from here, spent 5 months speaking gibberish. And it is time to solve the mystery from the top of this video. Come back to Pasadena with me. Same building. Same small cluster of offices at the Jet Propulsion Laboratory. 5 months after that November night, when Voyager 1 started talking in its sleep, the team has been living inside a 45-hour question and answer session all winter. Send a command Monday. Hear the result Wednesday. I think. Argue. Try again. Through December. Through January. Through February. The spacecraft kept transmitting its stuck, repeating pattern, and the engineers kept narrowing the search, ruling out one system at a time like doctors crossing diseases off a chart. And by early spring, they had their culprit cornered. The problem lived inside one chip. One chip, in the computer that packages Voyager's data for transmission, had gone bad. About 3% of that computer's memory sat on the broken chip, and the software that ran the whole system happened to route through that dead neighbourhood. The machine was healthy nearly everywhere. Its instruments worked. Its power flowed. Its radio held the link. But a critical stretch of its mind now lived on ruined ground, and every thought that crossed that ground came out scrambled. Now, what killed the chip? Hold that question, because the honest answer is coming. And the honest answer is the whole reason this chapter exists. First, you need to meet the suspect, because the suspect has been shooting at every spacecraft you have ever heard of, including the satellites over your head right now, and it will never stop. Space is full of bullets. They have no size you can picture, because they are single particles, atoms stripped down to their cores and flung across the galaxy by exploding stars. Some of them millions of years ago, some of them from suns that no longer exist. They travel at nearly the speed of light. They carry no light of their own, cast no shadow, make no sound, and they are passing through this room and through you. As you watch this, on Earth, we live under a planet-sized umbrella, our atmosphere and magnetic field, which soaks up or deflects almost all of it. A spacecraft leaves the umbrella on day one and never gets it back. Here is the part that matters. To a human body, this radiation is a slow medical problem. To a computer, it is a rifle. A modern memory chip stores information as electric charge in cells so small that millions of them would fit on a grain of rice. Each cell holds a 1 or a 0, and the difference between 1 and 0 is a whisper of trapped electrons. When a cosmic ray tears through a chip, it leaves a wake of electric charge behind it. And if that wake splashes into a memory cell, the whisper changes. A 1 becomes a 0 becomes a 1. Engineers call it a bit flip, and I want you to feel how eerie it is. Nothing breaks. There is no hole, no burn mark, no debris. Put the chip under a microscope afterward, and it looks perfect. The machine is physically untouched, and yet its memory now contains something that was never written there. One letter changed, in one word of one instruction, by a particle that arrived from another star and left without slowing down. Most bit flips are harmless. The flipped bit sits in some unused corner, or gets overwritten before anyone reads it. But sometimes the flipped bit is load-bearing. Sometimes it sits inside a command, or an address, or a piece of the operating system, and then a machine that was working flawlessly begins, without any warning, to do something strange. Satellites have tumbled because of single flipped bits. Space computers have crashed, rebooted, locked up, wiped data. One particle, one bit, one bad day. So how do you fight a bullet you cannot see, cannot block, and cannot predict? The space business has spent 60 years building its answer, and the answer has 3 layers. And the first layer explains something that puzzles everyone who hears it. The computers we launch into space are old. Deliberately. Proudly old. The processors flying on billion-dollar missions today are, by the standards of your phone, museum pieces. And the reason is beautiful. The smaller and denser a chip's circuits, the less charge it takes to flip a bit, which means every generation of faster, smaller electronics is also a generation of easier targets. Big, chunky, old-fashioned transistors take a real hit to flip, so space engineers buy toughness with age, using special radiation-hardened chips, built on wide old circuit designs, tested in particle beams on the ground, where engineers literally shoot at them with accelerators to see what it takes. Your phone would not survive a year of deep space. Voyager's museum piece brain has taken cosmic fire for half a century. The second layer assumes the first will fail, because it will. Space software wraps its memory in error-correcting codes, extra check bits woven through the data like a librarian, constantly walking the shelves, noticing that a book is out of place, and putting it back. A single flipped bit gets caught and repaired automatically, often before it can do anything. And the third layer assumes the second will fail too. Critical spacecraft fly multiple computers running the same calculations side by side, voting on the answer, so that one poisoned machine gets outvoted by its healthy twins. And beneath all of it sits the last resort. Safe mode. The instinct every spacecraft is born with. When a machine finds itself confused beyond repair, it stops, points its solar panels at the sun, points its antenna home, shuts down everything optional, and waits for instructions. A lost child standing still in the supermarket, doing exactly what its parents taught it. Layers on layers on layers. And now, with all of that in view, come back to the patient. Was Voyager's dead chip killed by a cosmic ray? Here is the discipline this channel owes you. Nobody knows. And nobody ever will. The team at JPL names 2 suspects. One is a particle strike, a bullet that finally landed after 46 years of fire. The other is simply age, a circuit from 1977 that wore out, an old soldier's heart giving up. There is no camera out there, no autopsy possible on a chip 15 billion miles away. And the engineers say both causes are plausible and neither can be proven. That uncertainty is the everyday truth of this work. Half a century into a mission, the bullets and the birthdays become impossible to tell apart. What the team did about it, though, is documented minute by minute, and it belongs on the short list of great repairs in engineering history. The broken chip could not be fixed, so the software living on it had to move. Simple to say. Now the constraints. The computer's total memory is about 69 kilobytes, roughly one nice photograph on your phone, and it was nearly full, with no empty region big enough to hold the homeless code in one piece. So the team cut the code apart, divided it into fragments, and hunted through the memory map for surviving nooks. A corner here, a gap there, tucking each fragment into whatever healthy space existed. Then, because the fragments could no longer sit side by side, they rewrote the connections, teaching each piece where its neighbours had moved, stitching the pathways back together by hand. They did this in an assembly language from the 1970s, consulting engineering documents older than most of them, with no simulator that fully matched the flight hardware, and every patch they sent crossed a 22.5-hour gap toward a machine that could not afford many more mistakes. They sent the first relocation in April of 2024, then the wait, a full round trip, almost 2 days of silence in Pasadena, and on April 20th, the garbage stopped. In its place came clean, formatted engineering data, readable for the first time in 5 months. The room at JPL erupted, people cheering, hugging, wiping their eyes over a telemetry screen. By June, the science instruments were back online too, and the oldest machine we have ever flown picked up its work as if the winter had never happened. Reading the thin breeze between the stars and reporting home. Update the patient's chart, because this is our second visit and the ledger matters tonight. Voyager 1. Age 46 at the time of the illness. Survived it. Level 5. Science. Restored. Level 4. Communication. Restored. But read the fine print the way the engineers do. 3% of the machine's memory is now dead ground. Permanently. And there are no spare chips coming. No transplant possible. Ever. The next flip bit, the next tired circuit, will be triaged the same way, by moving thoughts out of ruined rooms into a house that only ever gets smaller. The repair bought time. It did not buy the machine back. And keep one image from this chapter above all the others. Whatever killed that chip, bullet or birthday, it was invisible, silent, and smaller than anything you can picture. The farthest machine humanity has ever built was brought down for 5 months by something with no size, no sound, and no warning, which makes it time to change scales completely. Because closer to home, in the crowded sky right over your head, Spacecraft face the opposite problem. The bullets there are real. You can see them on radar. You can watch them coming, sometimes for days. And the terrifying thing about the real bullets is not what they are made of. It is how fast this neighborhood moves. Hold a snowflake in your mind. A fat, soft, Christmas card snowflake. The kind that lands on a child's mitten. Now, answer me this. Could a snowflake kill a spacecraft? Your gut says no. And your gut is using Earth rules. On Earth, light things are harmless things. Because nothing light ever moves very fast down here. A snowflake drifts. A paint chip flutters. A bolt drops off a truck and skitters to the shoulder of the road. Weight is what hurts. We learn that as toddlers, and we carry the lesson into every intuition we own. Orbit does not follow that rule. And the reason is a piece of physics you can feel in one sentence. The energy of a moving object grows with the square of its speed. Double the speed. 4 times the punch. 10 times the speed. 100 times the punch. And everything in low Earth orbit. Everything. The working satellites. The dead ones. The lost bolts. The flakes of frozen fuel. The chips of paint shed by 50 years of rockets. All of it is moving at about 17,500 miles per hour. That is not a typo, and it deserves an anchor. It is New York to Los Angeles in 8.5 minutes. It is 25 times the speed of a rifle bullet's sound. And when 2 orbits cross at an angle, the closing speeds can run far higher, because both objects bring their own 17,000 to the meeting. At those speeds, mass stops mattering very much. Speed is the weapon. A fleck of paint, a crumb of metal, a snowflake of anything, arrives, carrying the energy of something enormous. The famous demonstration sits in a window of the International Space Station. One of the station's quartz panes, a window astronauts photographed the Earth through, one day showed a fresh crater, a gouged pit surrounded by a halo of cracked glass. And when the analysis came back, the best candidate for the impactor was a flake of paint, likely shed from some rocket or satellite years or decades ago. A fleck you could balance on a fingertip. It hit chipping glass built to stop it. A slightly larger crumb, a pea-sized bolt fragment, meets a spacecraft with the energy of a hand grenade, and the sky is full of crumbs. Radar networks on the ground currently track tens of thousands of debris objects big enough to catalogue, everyone moving at orbital speed. And beneath the tracked population swims a vastly larger cloud of fragments, too small to follow and plenty big enough to kill. So how do you armour a machine against grenades made of paint? Here is where the story turns wonderful, because the answer was worked out in 1947, before anything had ever been launched, by an astronomer named Fred Whipple, and his answer sounds completely backwards. Do not build thicker walls. Thick walls fail. A hypervelocity fragment hits a thick plate and drills, focused, all its energy on one point. Whipple's idea was to hang a thin sheet of metal out in front of the real wall, separated by a gap of empty space, just a foil fence. Standing off from the hull, the incoming fragment hits that first thin sheet, and at 17,000 miles per hour, the collision is so violent that the fragment does not punch through so much as detonate. Shocked instantly into a spray of vapour and molten droplets, the spray then crosses the gap, spreading wider as it flies, and by the time it reaches the actual hull, it has gone from a bullet to a cone of hot mist, its fury smeared across a wide patch of wall instead of drilled into a point. The wall shrugs it off. Engineers call it the Whipple shield, and the modern versions stuff the gap with layers of ceramic fabric and bulletproof weave. But the soul of the design is unchanged after nearly 80 years. And it is this. The shield is mostly nothing. You defeat the bullet with a gap. Distance itself is the armour. The International Space Station wears the heaviest version of this armour ever flown. Hundreds of shield panels wrapping every module where humans sleep and work. And the station needs every layer. because it is the biggest target in the sky, and it has been up there, in the thick of the shooting gallery, for more than 25 years. Its true scars, though, come from a threat the shields cannot touch. And this is where our chapters start braiding together. Remember the oven and the freezer. 16 times a day. The station has taken that ride for a quarter century. Roughly 150,000 swings between fire and ice, while being yanked and torqued by every arriving and departing spacecraft. Dozens upon dozens of dockings, each one a slow-motion collision by design. Metal keeps score. Today, engineers on the ground track small cracks in parts of the station's oldest structure, watching them the way bridge inspectors watch a highway span, mapping, measuring, debating. The station is aging in real time, in public, and its retirement has a date with a decision attached to it. A strange and heavy decision we are saving for Chapter 15. Because what we have chosen to do with the station at the end of its life says everything about how this business thinks about death. For now, the station gives us one more gift. The best picture of what daily life in the shooting gallery actually looks like. Because when the radar networks spot a tracked object whose path will pass uncomfortably close, the station does something that still amazes me every time I think about it. It dodges. Flight controllers plan a burn, thrusters fire, and a structure the size of a football field, weighing close to 1 million pounds, politely steps out of the lane and lets the bullet go by. The station has performed dozens of these debris avoidance maneuvers across its lifetime, and they have become almost routine, penciled into schedules, executed between meals, and for the fragments too small to track, no warning, no dodge. There are only the shields, the gap armour, standing quiet watch around the sleeping crew. That is the arrangement over your head tonight. Dodge what you can see, absorb what you cannot, and even that is not the whole toll booth, because low Earth orbit charges one more fee, and this one is pure chemistry, slow and strange and invisible. The station's altitude is not quite outside the atmosphere. Nothing in low orbit is. Up there, the air has thinned to a ghost, but a ghost with a temper, because raw sunlight at that height splits oxygen apart. The comfortable 2-atom oxygen you are breathing right now gets torn into single atoms, and single oxygen atoms are chemically furious, desperate to grab the first thing they touch. A spacecraft at orbital speed sweeps through this thin, furious ghost constantly, each atom striking the leading surfaces and biting, one molecular bite at a time. Engineers call it atomic oxygen, and it works like sandpaper made of chemistry, gnawing at plastics, dulling paints, eating exposed films measurably over years. Early shuttle flights came home with surfaces visibly scoured by it, and it is a large part of why satellites dress the way they do, wrapped in those gold and amber foil blankets, coated in finishes chosen because the furious ghost cannot get a grip on them. That gleaming spacecraft look you know from every photo was never fashion. It is a hazmat suit, so tally up the neighbourhood, the paint grenades, the tracked bullets and the untracked swarm, the gap armour, the dodging, the sandpaper ghost chewing every leading edge. Low Earth orbit is the most convenient real estate in space and the most violent. A shooting gallery wrapped in a chemical bath, and machines that live there are being spent, continuously, from the day they arrive. Now zoom out and realise something about everything we have met so far. The vacuum's thievery, the thermal grind, the radiation, the debris, all of it shares one trait. It attacks the machine's body. The next killer is different, and the difference is why it deserves its own chapter. It does not strike, and it does not chew. It simply falls, softer than the snowflake we started with, one particle at a time, day after day, onto a machine that cannot brush itself off, and on a red plain 200 million miles from here. It spent 15 years losing a fight against a rover with a 90-day warranty. And then, in the summer of 2018, it stopped losing. It is time to go back to Mars and finish the story I interrupted in Chapter 3. Sol 90. Meridiani Planum. Mars. The rover Opportunity rolls across a plain the colour of an old penny. And back on Earth, its warranty expires today. This is the exact spot where I stopped the story in Chapter 3. So let me pick it up mid-heartbeat. The dust arithmetic said this machine should now be entering its final days. The fine red powder of Mars had been settling out of the sky since landing morning, exactly as predicted, layer by layer onto the solar panels. And the power readings had been sliding, exactly as predicted. The engineers in Pasadena were watching the decline the way a family watches a hospice chart. And then, over the course of a few nights, the chart did the one thing the arithmetic said it could never do. The power went up, not by a little. The panels came back like a patient sitting up in bed. Somewhere out on that plain, something had reached down and wiped the dust off. And after the confusion cleared in Pasadena, the answer turned out to be Mars itself. The same restless world that dumps dust on everything also breeds dust devils. Slender tornadoes of wind and grit that wander the plains by the thousand. And when one of those passed over or near the rover, its swirl vacuumed the panels clean. NASA had refused to put wind in the survival math, because you cannot promise weather, and no engineer signs a warranty that depends on being lucky. But Mars, it turns out, occasionally runs a car wash. The team called them cleaning events, and they became the heartbeat of the whole mission. Dust builds for months. Power sags. Everyone holds their breath. Then a gust or a devil sweeps through and the panels gleam and the death sentence gets postponed another season. On that rhythm, 90 days became a year became 5, 5 became a decade, and the machine with the 3-month warranty simply kept going, through everything Mars could think to throw, and Mars threw plenty, because dust does not only fall from above. In the spring of 2005, Opportunity drove into what looked like an ordinary ripple of sand and sank, all 6 wheels digging in, spinning uselessly, buried to the hubs in powder finer than flour, 200 million miles from the nearest tow truck. The team named the dune Purgatory, which tells you their state of mind, and the rescue is one of my favourite scenes in the whole space program. Because it happened mostly in California, engineers at JPL built a sandbox, filled it with a recipe of crushed rock and clay mixed to imitate that exact Martian powder, drove a twin rover into it, and spent weeks learning how to fail. Every escape trick was rehearsed in the sandbox first, wheel by wheel, until they knew precisely what worked. Then they sent the choreography to Mars a few feet at a time. It took more than a month of patient, rehearsed wiggling. Purgatory let go, and the rover rolled on. Winter was the other siege. Mars runs cold beyond anything in Alaska, and winter sunlight through dusty panels can drop below what the rover needs to keep its own electronics from freezing in the night. So the drivers learn to work the terrain like sailors working the wind, parking the rover on north-facing slopes, tilting its panels toward the low winter sun the way you would angle a lawn chair toward a sunset, and holding there for weeks, sipping light, waiting out the season. A machine warranted for 90 days learned to hibernate. Add up all of it. The car washes, the sandbox rescues, the winter camping, and the totals come out sounding like a misprint. The rover was designed to drive about 1 kilometre, roughly the length of 10 football fields. It drove more than 28 miles, and the team, knowing exactly what they were doing, steered those miles past the 26.2 mark and celebrated the first marathon ever run on another world. 90 days of warranty became almost 15 years of service. 5,111 Martian days. A machine outliving its promise by a factor of 60. On wind it was never allowed to count on. Then came June of 2018, and the sky itself turned against it. Dust storms on Mars are usually local, patches of weather that blow through and move on. An Opportunity had shrugged off dozens, but every decade or so, for reasons still not fully understood, the local storms link hands and grow until they swallow the entire planet. And the storm of 2018 became the thickest ever measured over that plain. Here is what a Martian dust storm actually is. And it is not what the movies show. The air of Mars is far too thin to knock anything over. A hurricane there would feel like a breeze on your cheek. The storm does not hit the rover at all. It turns off the sky. Dust lifted miles high, spreading in every direction, until the sun over Opportunity dimmed, browned, and disappeared. Scientists measure that gloom in a number called tau, and for perspective, a heavy, overcast day sits near tau 1. The storm over Opportunity passed tau 10, a murk so complete that high noon on Meridiani became darker than any night the rover was built to survive, and beneath that sealed sky sat a machine whose heart ran on sunlight. The batteries drained day by day, and the team knew exactly what the falling numbers meant. On June 10th, 2018, Opportunity radioed home a routine engineering report. Power falling, sky opaque, and went silent. In the days after, a reporter covering the mission translated that last dry telemetry into a single line of English, and the line went around the world. My battery is low and it is getting dark. I want to be straight with you, because this channel keeps its discipline. The rover never said those words. Machines do not compose farewells. That sentence is a human translation of a data packet. But I will also tell you that the original, the real message, a column of numbers reporting the light dying and the charge falling, is somehow colder and harder to sit with than the poetry ever was. The storm eventually cleared, as they always do. The sky brightened. The planes lit up again. And at JPL the recovery campaign began. They called on every channel the rover knew. They called on days when winds might have delivered one last car wash. They called through summer and fall and into the new year. More than 1,000 separate commands sent into the quiet. Each one a hand, knocking on a door 200 million miles away. Nothing came back. On February 12th, 2019, the team gathered for one final session, sent the last commands, and, this being a crew that loved its machine, played one last wake-up song into the deep space link, a recording of Billie Holiday singing "I Will Be Seeing You." Now run the scorecard, because this is the cleanest autopsy of the night so far. Opportunity exists. Level 1, intact, parked forever on the slope of a channel the team had named. Before any of this happened, Perseverance Valley, its wheels, its arm, its cameras, all of it stands there today, whole, under a slowly thickening coat of red. What died was level 2. Power. The storm starved the batteries. The cold likely finished the electronics during the blackout, and every level above 2 fell without a fight. Because in a spacecraft, everything above the heart is a tenant of the heart, and that is the pivot the whole night turns on. So let me say it plainly. The bullets, the ovens, the debris, the storms, all the violence of the first half of this video. Every one of those killers might get you and might miss you. Opportunity dodged them all for 15 years. What it could not dodge was starvation. From this chapter forward, the enemies stop arriving from outside. The enemies are already aboard, sealed in at launch, and they do not attack. They subtract. Welcome to the second half of a spacecraft's life, where nothing dramatic ever happens, and everything is being lost. And we begin with the master resource, the one that owns all the others, the one whose slow arithmetic is, at this exact moment, writing the ending for the most famous machine in this story. There is a version of this chapter that plays out in Florida every hurricane season. In the first quiet hour after the grid goes down, the house has a generator. Because this is Florida and the family has done this before. Dad gets it running. And then comes the meeting at the kitchen table. And the meeting is never about what the generator can power. It is about what it cannot. The refrigerator. Obviously. The air conditioning. In August. In Florida. Feels non-negotiable until you do the math. And the math says pick one. Refrigerator or air conditioning. Lights or television. The freezer full of groceries or the fans in the bedrooms. The generator hums along at its fixed little output. Indifferent. And the family discovers a truth every spacecraft is born knowing. When your power is capped, your whole life becomes a list of things ranked by how much they deserve electricity. Every machine we have ever launched lives at that kitchen table. Permanently. And everything aboard is negotiable except the power supply itself. So tonight, meet the only two bloodlines that have ever kept our spacecraft alive. The first bloodline is sunlight. And close to home, sunlight is glorious. It is free. It is everywhere. And it never runs out. Wrap a satellite in solar panels and you have a machine that eats daylight, which is why nearly everything orbiting Earth runs on it. But sunlight has a flaw hidden in plain geometry. It spreads, light leaving the sun fans out in every direction. And the farther you stand from the source, the more thinly it is spread when it reaches you. And the fall-off is brutal, running with the square of the distance. Stand twice as far away and you catch 1/4 the light. 5 times as far. 1/25. Jupiter sits about 5 times farther from the sun than we do. So at Jupiter, a solar panel collects about 4% of what it gathers at Earth. 4%. Imagine your paycheck cut to 4 cents on the dollar and being told to run the same household. When NASA sent the Juno spacecraft to Jupiter on solar power, a genuine first at that distance, the engineers had to build panels so enormous that the spacecraft became mostly wing. 3 great blades stretching out to span a machine wider than a basketball court. All of it labouring to harvest a trickle that a beach towel-sized panel could catch in Earth orbit. That is the tax at Jupiter. Go farther. To Saturn. To Neptune. Toward the space between the stars. And the arithmetic simply forecloses. Sunlight is a bloodline for the inner solar system only, and even where the light is strong, the panels themselves are dying. Radiation. Our sniper from Chapter 7 dims solar cells year by year, clouding them the way cataracts cloud an eye. Thermal cycling cracks their tiny connections. Dust, where there is dust, buries them. And you have seen where that ends. A solar-powered spacecraft loses a little of its income every single year of its life. A few percent. Steadily. Forever. And its operators plan around that, fading the way farmers plan around thinning soil. So for the deep dark, engineers turn to the second bloodline. And the second bloodline is the strangest and most beautiful power plant ever built. No flame, no moving parts, no sunlight, just a lump of a special metal, plutonium-238, sealed in a case, doing the only thing it knows how to do, which is decay. Its atoms fall apart on their own schedule, and every falling atom releases a whisper of heat, and the sealed lump glows warm from the inside, cherry hot, for decades, wrapped in devices that turn heat directly into electric current with no machinery whatsoever. Engineers call the whole assembly a radioisotope thermoelectric generator, an RTG, and you should think of it as a fire that cannot go out, burning nothing, needing nothing, a private ember that works identically in sunlight, in shadow, in the blackness past Neptune where the sun is just the brightest star. The ember comes with one condition, and the condition is the whole second half of this video. Radioactive decay obeys a clock no one can wind. Every year, a fixed fraction of the plutonium atoms are simply gone, spent, and the ember cools by that exact amount, on a schedule written into the metal before launch. Immune to clever engineering, immune to hope, an RTG does not fail. It fades, smoothly and precisely, like a tide going out on a timetable printed years in advance. Which brings us back, for the third time tonight, to the patient in Pasadena. When Voyager 1 left Earth in 1977, its 3 RTGs together produced about 470 watts. Sit with how small that already was. 470 watts is less than the microwave oven in your kitchen. The grandest voyage in human history. The machine that would cross the heliosphere and touch interstellar space. Departed with less electricity than it takes to reheat a bowl of soup. And from that first day, the tide has been going out at almost exactly 4 watts per year. 4 watts a year. Every year. For nearly half a century. No accident has ever touched Voyager's power supply. No repair has ever helped it. It is simply arithmetic. Subtracting. So the Voyager team has spent decades at the kitchen table. And their meetings have teeth. Everything optional went first. Years ago. Backup systems. Off. Instrument heaters. Off. Un by un. Each shutdown a gamble that the instrument would keep working in deepening cold. And several, wonderfully, stubbornly, did. Then the science instruments themselves went onto the list. Ranked. Debated. Mourned in advance. In the spring of 2025, the subtraction came for another of them, and the team commanded one more instrument dark to buy the rest a little more time. And by this year, 2026, Voyager 1 is down to 2 working science instruments. TFO, from a machine that once carried 11, each shutdown buys a few watts, and a few watts buys months. And that is the trade now. Permanently. Turn off a piece of the mission to keep a smaller mission alive. Run the arithmetic forward and it lands in the early 2030s. Somewhere around there. The fading ember will no longer cover the 2 bills that cannot be negotiated. The transmitter that speaks to Earth and the bare survival heat of the machine itself. The team says its goal, said plainly and publicly, is to carry these spacecraft across their 50th anniversary in 2027, and then as far past it as the watts allow. Nobody involved talks about saving the mission anymore. They talk about landing it, the way you would talk about a plane low on fuel, still flying beautifully, with a runway somewhere ahead that everyone aboard can see. Update the chart. Level 5. Science. Still alive tonight, and visibly narrowing. 2 instruments where 11 once ran. Level 4. Level 3. Level 2. All healthy. All living on a countdown measured in single-digit years. The oldest machine we have is not sick. That is what makes this chapter different from every chapter before it. It is simply running out. At 4 watts a year. On schedule. And now that the shape of that ending is in front of you, I need to complicate it. Because power is the master clock, but it is not always the first clock to strike. There is another tank aboard nearly every spacecraft. Filled on the ground. Sealed at launch. Spent gram by gram across the mission. And when it hits empty, the ending it delivers is stranger and crueler than a fading ember could ever be. Because a spacecraft that runs out of power dies like a candle. A spacecraft that runs out of the second thing dies healthy. Next chapter. A machine in perfect working order. Batteries charged. Computers fine. Instruments fine. Loses everything in a single week. And I want you to watch it happen closely. Because it is the purest spacecraft death there is. Out on Route 66, deep in the Mojave Desert of California, there is a stretch where the towns thin out and the gas stations sit 50 miles apart. And every summer, somebody's car proves the point of this chapter. Picture that car. It is a good car. The engine is strong. The battery is charged. The tyres are new. The air conditioning blows cold. And every gauge on the dash reads perfect except one. The needle on the fuel gauge is lying on its side. And so this healthy, capable, well-maintained machine rolls to a stop on the shoulder, and the desert silence closes over it. And nothing on that car is broken. Every system aboard would pass inspection. The car did not fail. It just cannot participate anymore. Now, I need you to hold that image. Because tonight, it is the key to the strangest kind of death in spaceflight. And to understand it, you first have to understand something that sounds like a riddle. Why does a spacecraft need fuel at all? It is not driving anywhere. Once a machine is on its course, the beautiful physics of orbit says it will coast forever. No engine required. No fuel burned. Momentum for free until the end of time. So a spacecraft coasting through the dark should need fuel the way a sailboat needs oars. Nice for emergencies. Hardly a matter of life and death. Here is what that riddle misses. And it is the single most underrated fact in this whole business. A spacecraft does not burn fuel to go. It burns fuel to point. Think about what pointing actually means for these machines. And start counting the jobs. The main antenna must aim at Earth. And from deep space. Earth is a target so small that the antenna beam has to hold within a fraction of a degree. Day after day. While the spacecraft drifts and turns under every tiny push the universe gives it. Sunlight itself pushes. Remember, we will see just how hard in a few minutes. The solar panels must face the sun, or the batteries starve. And you watched in the last chapter what starving looks like. The cameras and instruments must aim at their targets, or there is no science. No level 5. No reason for the mission to exist. Every one of those jobs is the same job. Hold the pose. And holding a pose. In a place with nothing to grab onto. No ground. No air. No wall to brace against. Costs you constantly. Most big spacecraft split that cost between two systems. For the fine, everyday holding, they use spinning wheels. And those wheels get their own chapter next. Because their story deserves it. But the wheels have a weakness. Push against them long enough and they fill up. Spinning faster and faster until they max out. Like a clock spring wound to its stop. And when a wheel is full, the only way to empty it is to fire tiny rocket thrusters in the opposite direction while the wheel unwinds. Engineers call it desaturation, and it means that even a perfectly designed spacecraft, doing nothing but holding still, must spend little sips of fuel on a regular schedule. Forever. The tank drains in whispers. A puff this week. A puff next week. Gram by gram across the years. And no cleverness on Earth has ever found a way around it. Because the fuel is not a convenience. It is the price of pointing. And pointing is the price of everything else. Which brings me to the spacecraft this chapter belongs to. And to one of the most impressive resumes in the history of exploration. In September of 2007, NASA launched a machine called Dawn toward the asteroid belt. And Dawn was built to do something no spacecraft had ever done. Every mission before it had been a drive-by or a single destination. Dawn was going to travel to one alien world. Stop. Orbit it. Study it for a year. And then, and this is the part that had never been done, leave. Cross deep space again. And go into orbit around a second alien world. 2 separate worlds. Orbited by one spacecraft. On one tank of everything. It could even be attempted only because Dawn carried an exotic ion engine for the long hauls. A gentle blue thrust that sipped its own separate fuel supply with legendary efficiency. But for pointing, for the everyday work of holding the pose, Dawn relied on the classic recipe. Spinning wheels for the fine control, and a tank of a chemical called hydrazine, feeding small thrusters for the desaturations and the backup. Dawn flew to the giant asteroid Vesta and orbited it beautifully. Then it did the impossible thing. Climbed away, crossed to the dwarf planet Ceres, and slid into orbit there too. The first spacecraft ever to orbit two different worlds. It mapped Ceres pole to pole and found, glowing in the middle of a dark crater, patches of brilliant white salt, the residue of briny water that had somehow reached the surface of a world that was supposed to be a dead rock. Water chemistry. On a dwarf planet, found by a machine on its second world. The mission was a masterpiece, but while the science soared, the machinery underneath it was quietly bleeding. Dawn's pointing wheels, those spinning workhorses, began failing years into the flight. One, then eventually more, and every wheel that died shifted more of the pointing burden onto the hydrazine thrusters. Sips became gulps. The flight team, and they were brilliant about this, rewrote the entire way the spacecraft operated to stretch what remained, inventing new flying techniques mid-mission, hybrid pointing schemes, careful rationing. They turned a crisis into years of extra science. And still, every week, the tank got lighter, and everyone involved knew exactly what that meant. Because unlike almost any other resource on a spacecraft, hydrazine offers no partial failure, no graceful fade. The RTGs of Voyager dim by percentages. A fuel tank works perfectly until the instant it does not. By 2018, the engineers could calculate the end almost to the week, and in late October of that year, right on the arithmetic, Dawn missed a scheduled radio session with the Deep Space Network. Then it missed the next one. The team ran the checks, ruled out the other explanations, and announced what they had long known was coming. The hydrazine was gone, and I want you to walk through what happened aboard that spacecraft in its final days, because this is the autopsy that explains the whole chapter. Nothing broke. Read that again. Nothing aboard Dawn broke. The computers were healthy. The batteries held charge. The instruments that had mapped two worlds sat ready for their next command. But with the tank empty and too few wheels left, the spacecraft could no longer fight the gentle pushes of sunlight and physics. And it began, slowly, to lose its pose. The great antenna drifted off its lock with Earth, and the link went quiet. The solar panels drifted off their lock with the sun, and the power began to die. Every downstream system failed in sequence, not from damage, but from abandonment. Tenants of a building whose landlord could no longer hold the door shut against the wind. Run the scorecard one last time and feel how strange this one is. Level 1. Existence. Perfect. Level 2. Power. Healthy at the moment of death. Doomed only afterward. Level 4. The radio. In working order with nothing to aim it. Level 5. Instruments. Flawless. Dawn died at level 3. Control. And level 3 alone. The purest single-level death in this entire video. It is the car in the Mojave. Every gauge perfect except one. And that one gauge owns the road. Dawn is still out there tonight. And this last detail is the one I cannot shake. It did not crash. And it will not. NASA deliberately left it in a high, stable orbit around Ceres. And here is why. Ceres, with its briny white salt and its hints of water, is exactly the kind of world we now protect. Because a dead spacecraft carries living stowaways, hardy Earth microbes sealed into its crevices since the launch pad. And if Dawn ever fell onto that surface, we could contaminate the one thing we went there to study. So the orbit was engineered to hold for decades at minimum. A quarantine measured in generations, keeping the sterile distance between the explorer and the world it loved. Hold on to that idea. A spacecraft's ending designed around protecting a world. Because in Chapter 15, it becomes the whole story. For now, close the file on Dawn with the lesson it died to teach. Power is the master clock, but fuel is the sudden one. A mission can see its ember fading years ahead. The tank just ends on a Tuesday and takes a healthy machine with it. And notice the shape of what actually happened here. Because Dawn's fuel crisis did not start in the fuel tank. It started upstream, in those failing wheels, small spinning things buried in the chassis. None of them much bigger than what you would find in a hardware store. The tank paid the bill, but the wheels ran up the debt. It is time to meet the wheels. Every American has fought the shopping cart. You know the one. 3 wheels rolling fine, and one front wheel with a mind of its own, shuddering, dragging, yanking the whole cart sideways every few steps. And here is the thing about that cart. It is 99% healthy. The frame is solid. The basket is fine. 3 of the 4 wheels are perfect. But nobody describes that cart as 99% good, because the truth of any machine lives in its smallest failing part. One bad wheel does not cost you 1 wheel's worth of performance. It costs you the cart. Now put that cart in space. Make the wheels spin at thousands of revolutions per minute. Seal them where no hand can ever reach, and make the nearest replacement 93 million miles away. That is this chapter. Not the fire, not the radiation, not the storms, the little spinning things. Because when you audit the great mission endings of the space age, you keep finding the same culprits, and they are always small, always mechanical, and always mounted somewhere no one can touch. Start with the strangest device on the list, the one that actually holds spacecraft still. It is called a reaction wheel, and it works on a principle you have felt in your own body. Sit in an office chair, feet off the floor, and twist your shoulders hard to the left. The chair swivels you to the right. You pushed against nothing, and you turned anyway, because momentum has to balance. A reaction wheel is that trick. Industrialized. It is a heavy metal disc, spinning fast. And when the spacecraft's computer speeds the disk up, the Homo spacecraft rotates gently the other way. Slow the disk down. The ship turns back. 3 or 4 of these humming disks, mounted at angles. Let a machine point anywhere in the sky with exquisite precision. No fuel burned, just electricity and spin. They are the fingertips of every great observatory, and they carry a curse. They are bearings, spinning at speed, running for years, in vacuum, where we already know what happens to lubricants. Chapter 5 never went away. Every reaction wheel in space is running a marathon on oil that is slowly leaving, and so we come to the greatest planet hunter ever built, and the best comeback story in this whole video. In March of 2009, NASA launched a space telescope called Kepler, and Kepler's job description was almost insultingly simple. Stare. That is the whole job. Stare at one single patch of sky, about the size of your open hand held at arm's length, a patch containing roughly 150,000 stars, and never look away, and never waver. For years, Kepler was hunting planets around other suns, and its method demanded stillness beyond anything ever flown, because it found planets by catching the tiny dimming of a star when a planet crosses its face. And tiny does not begin to cover it. For a planet like Earth crossing a star like the Sun, the star dims by about 1 part in 10,000. That is a porch light across town, dimming for a few hours because a moth flew past it. To measure that, the telescope cannot drift by a hair. Kepler's stillness was the mission, and its stillness lived in 4 reaction wheels. For 4 years it was perfect. The little telescope stared at its patch, and the planets poured out. Hundreds of them, then thousands, worlds of every size, and the census changed astronomy forever, because it showed that planets outnumber stars in our galaxy. Then, in July of 2012, wheel number 2 began to grind. Metal fatigue. Friction. The marathon catching up. The team shut it down. Kepler could still hold its pose on the 3 survivors, and 3 was exactly enough. And everyone in the room knew the arithmetic had no slack left in it. For 10 months the telescope stared on, 3 wheels humming, no margin. And in May of 2013, wheel number 4 seized, 2 wheels left. And 2 is not enough. The telescope that defined stillness began to drift, and the mission was declared over. The spacecraft was healthy. The optics were flawless. The camera, the computers, the radio, all fine. It was the shopping cart, 93 million miles out. Dead in the aisle, over 2 spinning discs the size of dinner plates. And then somebody at the ball had an idea that belongs in a museum. The problem was that Kepler needed a 3rd point of stability and owned only 2. The insight, worked out by engineers at Ball Aerospace with the mission team, was that a 3rd stabilizer did exist aboard. One nobody had installed. Sunlight. Light itself pushes. It is the gentlest force you can name. Pressure so faint you will never feel it, standing in a summer noon. But it is real. And it never stops. And it was already pushing on Kepler every second, which until now had only made the drifting worse. The engineers asked a beautiful question. What if the push could be made to hold the telescope instead of tip it? Here is the trick. And it costs nothing. Orient the spacecraft so that sunlight falls perfectly evenly across its long solar panels, balanced like a canoe under a steady wind coming from straight astern. Any tip to one side exposes more surface on that side, catches more push, and gets nudged back level. The pressure of light becomes a self-correcting cradle around one axis, the exact axis the dead wheels had abandoned. Sunlight itself, drafted as reaction wheel number 3, holding the pose from 93 million miles away. It worked. It genuinely worked. The reborn mission was named K2, and it came with a price the team accepted gladly. Kepler could no longer stare at its beloved original patch, because the balancing trick only functions in certain orientations to the sun. So the telescope became a nomad, staring at a new field for about 80 days at a time, then rotating to keep the light balanced. The nomad years lasted 5 more seasons and found hundreds more worlds, planets discovered by a telescope leaning on a sunbeam. And the ending. When it came in October of 2018, the same month Dawn went silent, was not the wheels at all. Kepler ran out of thruster fuel. The same death you just watched in the Mojave. The wheels ran up the debt. The tank paid the bill. Those 2 chapters are one story, and the space business knows it by heart. Now, one more machine belongs in this chapter, because it carries the answer to a riddle I planted back in Chapter 2. I told you then that the number of times human hands have repaired a spacecraft beyond Earth orbit is 0, and I promised one glorious exception closer to home. Here it is. The Hubble Space Telescope has been in orbit since April of 1990, and Hubble's pointing depends on gyroscopes, small spinning sensors that tell the telescope which way it is facing and how fast it is turning. The inner ear of the machine. Gyros wear out the way reaction wheels do. Spin, bearings, years, vacuum, and Hubble eats them steadily. It launched with 6. And here is what makes Hubble unique in all of spaceflight history. When its gyros died, people went and got them 5 times. Between 1993 and 2009, astronauts rode the space shuttle up to Hubble, caught it with a robot arm, anchored their boots, opened its access panels in orbit, and swapped its failing organs by hand. Gyros, batteries, computers, whole instruments, the only spacecraft in history to receive surgery in the field. That is why a telescope designed in the 1970s is still working today. It is not that Hubble does not age. It is that Hubble, alone among all our machines, had visitors, had past tense. And the past tense is the point. The shuttle retired in 2011, and no vehicle flying today can bring a crew back to that telescope. Since the last service call, Hubble has been alone like everything else, spending down the 6 gyros from its final tune-up, and they have been failing on schedule, by across the years. By 2024, the working count was down near the bone, and the operators made a quiet, disciplined choice. Hubble now runs in 1 gyro mode, deliberately operating on a single gyroscope, while another healthy one sits switched off in reserve, saving it. The way you would bank your last good years. The telescope points a little slower now, tracks a little less nimbly, and it is expected to keep doing science well into the 2030s on this careful ration. There is a phrase for what Hubble is doing, and it is the phrase this whole chapter has been walking toward. The greatest telescope in history is limping on purpose, because limping, managed wisely, is a way of walking that lasts. So look at the pattern across these 3 machines, because it is one pattern: Damn, Kepler, Hubble. In every case, the grand instrument was fine and the small spinning part gave out. In every case, the first response was not repair, because repair is impossible. It was reinvention. New ways of flying. Sunbeam cradles. Deliberate limps. The machines age in their joints. And the people answer with imagination. That trade, where versus wit, is the true daily life of every long mission humanity runs. But there is a place where that trade breaks down, where wit runs into a wall. And the wall is not mechanical at all. Wheels and gyros are the body. What happens when the aging reaches the mind? What happens when the computer itself, the thing that runs the safe modes and executes the clever workarounds, becomes the failing part, on a machine so old that the people who understood its mind are gone, and so far away that a single conversation takes 2 days? That is not a hypothetical. That is a job description, held right now by about a dozen people in Pasadena. And one of the things they had to do recently was wake a system that had been asleep since 2004, knowing that waking it wrong could end the whole story. Time to visit the patient again. Somewhere in the buildings of the Jet Propulsion Laboratory, there are rooms most visitors never see. And inside those rooms are cabinets. And inside the cabinets is the memory of the Voyager mission. Not the computer memory. The paper kind. Design documents typed on typewriters. Engineering drawings inked by hand. Memos from 1974 arguing about circuits. Signed by men who have been gone for decades. Sheets of microfiche. That almost extinct format where whole manuals shrink onto film cards you read with a magnifier. When something breaks on Voyager today, this is where the trail leads. Because the machine flying out past the edge of the solar wind was built by people who documented everything and then, over half a century, retired, scattered, and passed away. The current flight team, a dozen or so people, some of them decades younger than the spacecraft, have described the job with a phrase I love. They are working with ghosts. To fix the machine, you sometimes have to find the right cabinet, pull the right folder, and read the handwriting of the person who understood this circuit best, knowing you cannot call them, because the mind that held the answer is gone and the paper is what remains. This chapter is about what happens when a machine grows so old that keeping it alive becomes a kind of archaeology. Start with what aging actually means for electronics, because it's quieter than you think. Nothing rusts up there. Nothing rots. But a circuit built in 1977 has been soaking in cosmic radiation for 49 years, and the total dose adds up, shifting the behavior of transistors by whispers, dimming their margins, Solder joints, thousands of them, have ridden decades of thermal swings. And Mel keeps score. Memory accumulates dead cells, the way we watched in Chapter 7. And every dead cell shrinks the house the software lives in. None of this announces itself. An aging spacecraft does not sputter like an old truck. It just becomes, year by year, a machine where more things are almost broken, where the margins everywhere are thinner, where each new fault lands on a system with less slack to absorb it, and the software ages in its own strange way. Voyager's code was written in assembly language for computers with about 69 kilobytes of memory, and I will renew that number's anchor, because it never stops being absurd. 69 kilobytes is less than a single photograph on your phone. The programmers who wrote for that world practiced an economy that borders on poetry. Every instruction counted, every byte justified, and the result is code so dense and so intertwined that changing any line means understanding what every neighbouring line assumed in 1977. There is no updating this software the way your phone updates overnight. Every patch is surgery on a living patient, performed through a straw, from 15 billion miles away, which brings us to the events of 2025, and the fourth visit to our patient, and the strangest wake-up call in the history of engineering. Here is the situation the team faced. Voyager 1 holds its pose using small thrusters, and among them are roll thrusters, the ones that rotate the spacecraft around the axis of its antenna, keeping it locked on a guide star so the dish stays pinned to Earth. Voyager carries a primary set and a backup set. In 2004, the heaters that keep the primary roll thrusters warm failed, and without heaters, a thruster in deep space is a frozen pipe. The team did the sensible thing. They switched to the backup set and wrote the primaries off. Dead. Retired. And for 21 years, the backups did the job. But the backups have been developing a problem of their own. And it is a problem with a clock on it. Every time a thruster fires, it leaves behind a whisper of residue in its fuel line. And across decades of tiny pulses, that residue builds like plaque in an artery. The tubes feeding the backup thrusters have been narrowing, year after year. And the team could see the day coming when they would clog completely. When that day comes, the spacecraft loses its grip on the guide star. The antenna wanders off Earth, and the conversation ends, no matter how much power the Ember still makes. So the engineers faced a choice that sounds like a riddle. The working thrusters are slowly clogging. The clean thrusters have been frozen dead for 21 years. And then somebody asked the question that saved the mission. Are we sure the primaries are actually dead? The team went back through the ghosts, back through the records of the 2004 failure, and built a theory. Maybe the heaters had not burned out at all. Maybe a switch in the heater circuit had simply been knocked into the wrong position. And if that was true, the fix was almost laughably simple. Flip the switch back. But the stakes attached to that simple fix were anything but laughable, because warming those heaters carried a genuine danger. If the spacecraft drifted enough during the process that its systems tried to fire the still frozen thrusters, the result could be a rupture, a small explosion in the plumbing, the kind of wound a machine that old does not survive. They would be reaching into a patient's chest to restart a heart that had been still since 2004, knowing that one wrong reflex could end everything, and there was a deadline, which is the detail that turns this story into a thriller. Commanding Voyager requires enormous radio muscle, and the dish that does that work is a giant in Australia. Antenna DSS 43 at the Canberra station, a 230-foot monster that is the only transmitter on Earth with the power to reach the Voyagers with commands. And DSS 43 was scheduled to go dark, shutting down for months of long overdue upgrades. If the backup thrusters clogged while the big dish was offline, the team would be standing in Pasadena, watching the spacecraft drift, holding a fix they could not send. The wake-up call had to happen before the phone line went down. In March of 2025, they sent the commands, flip the circuit, warm the heaters, then the ritual this mission has made famous. The 46-hour wait. A question crossing to the edge of interstellar space, and the answer crawling back. The data arrived. The heaters were warming. The switch theory was right. The thrusters declared dead for 21 years were alive, warmed, and ready to serve. And when the great dish in Australia went silent for its renovation, Voyager 1 held its pose with a backup for its backup, revived by people reading the notes of the dead. Update the chart from this fourth visit, and notice how the entries have changed in character. The early chapters of this video were about surviving events. This chapter has no event in it. Nothing hit the spacecraft. Nothing broke suddenly. The two stories of Voyager's recent years, the memory relocation of 2024 and the thruster revival of 2025, are both the same kind of story. The machine is wearing out everywhere at once, gently, and the people are answering with archaeology and nerve, buying months and years with folders and switch flips. Every rescue works, and no rescue reverses anything. The clogged lines are still clogging. The dead memory is still dead. The ember still fades at 4 watts a year. The patient's chart now reads like what it is. The file of someone very old and very far from home, tended by people who know exactly how this ends and refuse to let it end today. But there is one system we have not examined yet, and it is the one that makes all the others matter. Power can flow, thrusters can point, computers can think, and none of it counts for anything unless the machine can still be heard. The voice is the mission, and the voice of Voyager 1 is a whisper that has been growing quieter for 49 years, stretched across a distance that light itself takes nearly a full day to cross. How faint can a voice get before it stops being a voice at all? The answer is waiting in the California desert, under some of the largest ears human beings have ever built. Drive out of Barstow, California, into the Mojave, past the last gas stations and the Joshua trees, and eventually, in a bowl of dry hills on restricted government land, you will find them, giant white dishes, tilted at the sky, slowly turning. The largest is 230 feet across, a bowl you could pour a small stadium into, and it moves with the deliberate grace of something enormous listening very hard. This is Goldstone, one of the 3 ears of NASA's Deep Space Network, and the network's geography is a quiet masterpiece. 3 stations: Goldstone in California, another outside Madrid in Spain, a third near Canberra in Australia, spaced almost exactly evenly around the planet, 120 degrees apart, sit with Y. The Earth turns, and any single antenna spends most of the day facing the wrong way. But 3 stations, spread like that, mean that as one rotates away from a spacecraft, the next rotates toward it, and coverage never breaks. It is the whole planet, engineered into a single head that never turns its back on its machines. Every deep space mission you have ever heard of, every rover, every orbiter, every probe in the dark talks to Earth through these 3 sets of ears, and nothing else. And the hardest job those ears have ever had is the one this chapter is about. Hearing Voyager. Here is the physics, and it is merciless. A radio signal spreads as it travels, exactly like light from a bulb, thinning over distance. And the thinning follows the same square law that starved the solar panels in Chapter 10. Double the distance. 1/4 the strength. 10 times the distance. 1/100th. Voyager 1 is 15 billion miles out, and its transmitter puts out about 23 watts, which was a respectable radio in 1977 and is, in honest modern terms, the power of the light bulb in your refrigerator. Now, stretch that refrigerator bulb's glow across 15 billion miles of spreading, and ask how much of it actually lands in a 230-foot bowl in the Mojave. The The answer is a number so small it stops meaning anything. So let me build it carefully. Take 1 watt, divide it by 1,000,000,000. Now take that billionth and divide it by 1,000,000,000 again. The signal Goldstone catches from Voyager 1 is weaker than that. 1,000,000,000th of 1,000,000,000th of a watt, and less. All the energy that Dish has collected from Voyager across decades of listening, added together, every session, every year, would not light that refrigerator bulb for a flicker of a second. That is what the ears are working with. That is the voice, pulling information out of a signal that faint is one of the great unsung achievements of our species. And the method matters to our story. The dish gathers those scraps of radio energy and feeds them into amplifiers chilled to within a few degrees of absolute zero. Because at these signal levels, the random heat jitter of the receiver's own atoms is louder than the message. And the only way to quiet your own equipment is to freeze it nearly to death. Then the computers take over. And they already know the shape of what Voyager's transmissions are supposed to look like. The timing, the structure, the mathematical skeleton. And they use that knowledge to sift the true signal out from underneath the static. The way you can pick your child's voice out of a roaring playground because you know exactly what you are listening for. The signal is buried below the noise, and mathematics digs it out. Every session, on schedule, but there is no free lunch in that miracle. And the price is speed. When a voice is that faint, you cannot talk fast. For the same reason you slow down and repeat yourself on a phone call with terrible reception. Every bit needs time to be heard through the hiss. Voyager 1 today sends its science home at a rate measured in dozens to a few hundred bits per second. Let me place that. The screeching dial-up modems of the 1990s, the ones that tied up the family phone line, ran hundreds of times faster. The most distant voice humanity owns is speaking to us hundreds of times, slower than the internet of 1995. And every year, as the distance grows and the power fades, the conversation gets slower still. Now bring back the scorecard. Because this chapter has been quietly building to a point about it. And the point deserves to be said plainly. Level 4, communication, is the only level on the card that does not live on the spacecraft. Every other level is out there. Existence, power, control, science. All of it rides aboard the machine, succeeds or fails aboard the machine. But a conversation has two ends, and level 4 lives in the gap between them. It depends on the transmitter out there. Yes, and it depends equally on the ears down here, on the size of the dishes, the cold of the amplifiers, the cleverness of the sifting, the simple decision of whether anyone points a dish that way at all, which means something strange and important. A spacecraft can die at level 4 while remaining perfectly healthy at every level it controls. Picture the far future of any long mission. The machine still exists, still has some power, still holds its pose, still transmits, faithfully, into the dark. But the whisper has thinned past what any ear on Earth can dig out of the noise. Out there, nothing has changed. The voice is still speaking. It is simply speaking below the floor of our hearing. And from our side of the gap, the mission is over. The death did not happen on the spacecraft. It happened here, in a desert in California, in the gap between a whisper and an ear. And because level 4 lives on our side, it is subject to something no other level faces. Our choices. The Deep Space Network is a shared resource, and it is drowning in demand. Those 3 stations serve dozens of missions at once. Everything at Mars. Everything in deep space. The new flagship missions with their floods of data. All of them lining up for hours on a fixed set of antennas. And there are only so many hours in a day. Mission teams request time the way farmers pray for water rights. And the network's schedulers perform triage every single week. A young mission at Jupiter, with fresh instruments and a loud, clear signal. An old probe whispering from the edge. needing hours of a giant dish's day to deliver a trickle of bits. Both are worthy. Both cannot always be served. The listening itself has become a rationed resource. And for the oldest and faintest voices, the ration is part of the countdown, as real as the plutonium. It is an uncomfortable truth, and it belongs in this video, somewhere in the final ledger of every aging mission. Alongside the fading watts and the clogging fuel lines, there is a line item that has nothing to do with space at all. It reads, "Hours of Earth's attention," and it is not infinite. Follow that thread one step further, though, and it leads somewhere darker and more interesting than scheduling. If the listening is a choice, then the ending can be a choice. And it turns out that some of the most famous mission endings in history did not happen because a machine failed, or faded, or fell silent on its own. They happened because people in a room, after long deliberation, decided that a healthy spacecraft had to die, picked the date, planned the method, and carried it out. There is a night in September of 2017 when a room full of engineers in Pasadena stood up and applauded a signal for going flat. They had just killed one of the greatest machines ever built, on purpose, and they were right to do it. That story is next. 4:20 in the morning, September 15th, 2017, Pasadena, California. Mission control at the Jet Propulsion Laboratory. And the room is full at an hour when rooms are never full. On the screens, a green trace of radio signal, steady as it has been for 20 years. It is coming from Cassini, the spacecraft that has spent those 20 years at Saturn. And everyone watching knows two things about that trace. It is perfect, and it has minutes to live. The people in this room planned what is about to happen. They chose the date. They calculated the exact trajectory. They aimed their own spacecraft, healthy and obedient, at the one place it could never survive. And this morning it is following their orders flawlessly. At about 4:55, the trace wavers. Then it flattens into noise, and the room stands up and applauds. You need the whole chapter to understand that applause. So let me start with the question that produced it. Because the question is not what killed Cassini. The question is why the people who loved it most decided that it had to die. By 2017, Cassini was old and thriving. Its cameras worked. Its instruments worked. Its radio sang across 1 billion miles like it was nothing. But its fuel, the hydrazine that held its pose, was nearly gone. And you have already watched that movie. You know from dawn exactly what happens next. The tank empties, the pointing fails, and the machine becomes a derelict, coasting wherever physics carries it, uncontrolled, forever. For most missions, that ending is just sad. For Cassini, it was dangerous, and the danger had a name, Enceladus. Years earlier, Cassini had made what might be the most consequential discovery of its entire mission. Flying past this small white moon of Saturn, it found geysers, plumes of water erupting from cracks near the South Pole, venting into space from an ocean of liquid water sealed beneath the ice. Cassini flew through those plumes and tasted them, and the readings showed salts and organic chemistry, the ingredients list of a habitable world. A moon of Saturn, of all places, turned out to hide one of the most promising environments for life beyond Earth that our species has ever found. Now put the two facts side by side. A spacecraft about to lose steering, orbiting in the same system for eternity, and a nearby ocean world that might be inhabited. A derelict Cassini would loop through the Saturn system uncontrolled for centuries. And over centuries, orbits drift and chances add up. And one day, maybe long after everyone in that control room was gone, the dead machine could strike Enceladus. That alone might sound harmless. A sterile hunk of metal hitting distant ice. Except Cassini is not sterile. No spacecraft is. Every machine we launch carries stowaways. Hardy Earth bacteria sealed in its crevices and blankets since the assembly building. And some species of Earth microbe are terrifyingly good at surviving space. Years of vacuum and radiation and cold. Dormant, but not dead. If a contaminated spacecraft ever crashed into that hidden ocean's ice, we could seed an alien world with Earth life. And then, decades later, when some future mission finally lands there and finds microbes, we would face the most heartbreaking question in science. Did we just discover life? Or did we just discover our own garbage? Protecting against that outcome is a formal discipline called planetary protection. It is written into international agreements, and it gave the Cassini team their answer. The spacecraft could not be allowed to die at random. While it still had fuel, while it still obeyed, it had to be steered to an ending that could never threaten the ocean. And in the whole Saturn system, only one destination guaranteed that: Saturn itself, a planet of crushing bottomless atmosphere where nothing survives entry, where every molecule of the spacecraft would be scattered harmlessly into a world of gas. Cassini would be cremated in the very planet it had studied, so that Enceladus could stay clean for whoever comes next. Here is where the story turns from grim to glorious, because once the team accepted the ending, they asked a magnificent follow-up. If the spacecraft has to dive into Saturn anyway, what can it do on the way down? The answer became known as the grand finale, and it was the boldest flying of the entire 20-year mission. Between Saturn's cloud tops and the inner edge of its rings lies a gap, a corridor about 1,500 miles wide that no spacecraft had ever dared enter, because threading it means flying between a planet and its rings at tens of thousands of miles per hour. And one pebble-sized ring particle at those speeds is a cannon shell. Mission planners had always treated the gap as suicide. Now suicide was the plan. So the calculus flipped. In April of 2017, Cassini threaded the gap for the first time, survived, and then did it again, and again. 22 orbits in total, skimming closer to Saturn than anything in history. And the science poured in. It measured the rings from underneath, sampled the planet's outer atmosphere directly, mapped gravity and magnetism at point-blank range, data that could never have been gathered any other way, because no mission with a future would ever take these risks. The dying spacecraft spent its final months doing the finest work of its life, spending its last fuel on discoveries that only a doomed machine could afford. And then the last morning came, and the detail that gets me every time is what Cassini was doing during its final minutes, as it fell into Saturn's atmosphere and the thickening gas began to shove it around. The spacecraft did not tumble, and it did not flail. It fired its thrusters continuously, fighting to keep its antenna locked on Earth, streaming data live from inside the atmosphere of Saturn. Holding the pose, we have spent this whole video learning to respect, until the gas finally overwhelmed the thrusters and the antenna swung away mid-sentence. The signal on the screens in Pasadena flattened at that instant. The machine itself lasted seconds longer, breaking apart, burning, becoming part of the planet. It transmitted to the very edge of existence. Run the scorecard one final time for Cassini and read how backwards it is. Level 5. Science. Active in the final second. Level 4. Alive to the final second. Level 3. Fighting to the final second. Levels 1 and 2 were annihilated in flight, while everything above them still worked. It is the only death order like it in this entire video. Every level alive until all of them ended at once. And that inversion is exactly what the applause was for. The clapping in that room was not for a signal going flat. It was for a plan, carried out to the last breath, by a machine that never once disobeyed. Cassini is the masterpiece of chosen endings, but the choosing itself is everywhere in this business, and it comes in 3 flavors. So let me give you the other 2 quickly. Closer to home, there is a bureaucratic flavor. almost tender in its practicality, high above Earth. At the altitude where communications satellites live, there is no atmosphere to drag anything down. Ever. A dead satellite there stays forever. A hazard drifting through the busiest orbital real estate we own. So the rule, agreed across the industry, is that a satellite nearing the end must save its last sips of fuel for one final climb, a couple of 100 miles up, into an emptiness nicknamed the graveyard orbit, a parking lot above the working world where retired satellites are sent to circle, powered down, out of everyone's way, for millions of years. Hundreds of machines are up there right now, a silent fleet of the decommissioned, and the number grows every year. It is the strangest cemetery humanity keeps, and the only one visible from every point on Earth, and for the machines too big and too low for the graveyard. There is a wetter destination, in the South Pacific, at the point in the ocean farthest from any land, farther from humanity than the astronauts on the space station passing overhead. There is a patch of sea that spacecraft operators call Point Nemo. It is the official drop zone for the giants, chosen precisely because nothing and no one is there. Controlled deorbits have been aiming large spacecraft at those waters for decades, and the seabed below holds the shattered remains of hundreds of vehicles, including the Russian space station Mir, brought down deliberately in 2001, and here is the appointment to mark in your calendar, because we flagged it back in Chapter 8, the International Space Station, the biggest thing we have ever built off the planet. 400 tons of laboratories and trusses and memories. A quarter century of scarred, cracked, heroic service is scheduled to make that same final dive around 2030. NASA has already contracted the vehicle that will push it down. The largest spacecraft in history will end as a streak of fire over the emptiest water on Earth. And it will end that way because we chose it, planned it, and hired the executioner ourselves. Step back and look at what this chapter actually is, because something has quietly inverted. For 14 chapters, death was the enemy. The thing the engineers fought with sandboxes and sunbeam tricks and folders full of ghost handwriting. In this chapter, death became a tool. A well-aimed ending protects an ocean world. A graveyard orbit protects the working fleet. A splashdown at Point Nemo protects every roof between here and the sea, the mark of a mature spacefaring species. It turns out, is not just machines that survive. It is knowing precisely when and how they should stop, which leaves one machine unaccounted for, the one whose ending nobody gets to choose. There will be no grand finale for Voyager 1. There is nothing out there to protect it from, no ocean to shield, no fleet to endanger, nothing ahead of it for 10,000 lifetimes. There will be no last dive, no cremation, no applause at 4 a.m. There will just be a day, sometime in the coming years, when the ember under the floor finally cannot pay its 2 last bills, and the oldest conversation our species has ever kept simply stops. Nobody knows the date, but everybody on that team knows it is close. And it is time we walked through what that last morning will actually look like. The morning will start like every other morning in Pasadena. Coffee, badge at the gate, a handful of people at desks that have hosted this same quiet work since before some of them were born. I cannot tell you the date. Nobody can. The team's public goal is to carry both Voyagers past their 50th launch anniversary, which arrives in 2027, and then as far beyond it as the arithmetic allows. And the arithmetic points somewhere into the early 2030s before the power runs out entirely. So the morning I am about to describe sits a handful of years from tonight, close enough that the people who will live it are already on the payroll. Everything in this chapter is built from the mission's own projections, and from the way these machines have actually died before. Call it a forecast, not a prophecy. Here is how the forecast goes. First, in the years before that morning, the mission narrows. You have already watched this part begin. The instrument shutdowns of 2025 and 2026 were not emergencies. They were the plan. And the plan continues. One instrument dark, then another. Each shutdown buying the survivors a few more months of watts. Level 5. Science. Does not die on Voyager. It tapers. Deliberately. Like a household selling furniture room by room. Until the day comes when the last instrument is spending more power than the Ember can spare. Somewhere in the late 20s or early 30s. The team will send a command they have been drafting in their heads for years. And Voyager 1 will become a voice with nothing left to report. A pure carrier of its own continued existence. Even then, that signal will be worth hearing. Proof of life from farther away than anything has ever spoken. Then the voice itself starts to starve. The transmitter needs its ration of watts. The pointing system needs its ration. The bare survival heat needs its ration. And the Ember, remember, subtracts 4 watts every year without exception. The margins that were thin become paper. And here is where the real world will intrude on the tidy arithmetic. Because a machine running that close to the edge does not fail on schedule. It fails on a bad day, a cold snap in some component, a brownout that trips a fault, a safe mode. That lost child instinct from Chapter 7, triggered by some threshold, crossed at 3 a.m. Pasadena time. The team will do what they have always done. Diagnose through the 46-hour round trip. Dig through the ghost folders. Find the workaround. Until one time, the workaround needs more power than exists. That is how the forecast actually ends. Not with a planned farewell, but with an ordinary anomaly that turns out, after weeks of trying, to be unfixable, and the fixes themselves costing power the machine no longer has. We have watched this exact ending before, and it is worth remembering how quiet it was. Pioneer 10, Voyager's trailblazing older cousin, faded through the early 2000s precisely this way, its signal thinning year by year until the great dishes were digging a whisper out of the static. Its last confirmed signal reached Earth in January of 2003, and after that, nothing but noise. There was no explosion, no final massage, no moment you could point to and say, there. That is when it died. There was just a scheduled listening session where the signal did not rise above the floor, and then another, and then the decision to stop scheduling them. And you already know the other version, the opportunity version. The door knocked on more than 1,000 times. The last commands. The recovery campaign that ends with a decision rather than a discovery. One of those two shapes is waiting for Voyager 1, a silence that arrives mid-conversation, or a silence confirmed by calls into the dark. Either way, the morning comes, the session where nothing rises out of the noise, the checks, the reruns, the second station brought in to be sure, the meetings that follow, the attempts that follow, and eventually, weeks or months later, the announcement that the mission that outlived its planet's own century is over. It will be a Tuesday or a Thursday or whatever it is, and the news will run everywhere, and every headline on Earth will say the same thing. Voyager 1 is dead, and every one of those headlines will be wrong. This is the turn the entire video has been building toward, so I want to slow down and take it carefully. Pull out the scorecard from Chapter 2, the 5 levels, and run the audit on the machine. Those headlines will be mourning. Level 5, Science, dead. Yes, tapered away years earlier by deliberate command. Level 4, Communication, dead. The whisper below the floor of every ear on Earth. Level 3, Control, dying or dead. Because with no power for the pointing system, the antenna wanders and the pose is finally lost. The thing it held for half a century released at last. Level 2, Power, a cooling ember, below every threshold that matters, fading toward nothing across the following years. Level 1, The machine itself, the 1,100-pound body of titanium and aluminum, the dish, the booms, the instruments, the folders of dead men's handwriting made metal, untouched, completely, perfectly untouched, and headed nowhere near danger for longer than you can imagine. Think about what is actually out there where Voyager 1 is going. Every killer in this video, every single one, is a local. The launch violence lives on launch pads. The thermal grind lives near stars, where there is fire to swing in and out of. Atomic oxygen lives in the fringe of an atmosphere. The debris shooting gallery lives in the crowded shell around a planet. Dust lives on worlds. Even the slow killers, the fading panels and emptying tanks, they only matter to a machine that is trying to do something. Voyager 1, silent, is done trying, and the neighbourhood it is entering has none of it. No air, so nothing can ever rust or corrode. No weather, no water, no wind, so nothing erodes, nothing to hit, because it is leaving every crowded region behind, and the space between the stars is emptier than the emptiest vacuum chamber ever built on Earth. Nothing to fall onto, because it is falling toward nothing, moving at 38,000 miles per hour, faster than anything needs to catch it, on a path that owes gravity no debts it cannot pay. The morning the headlines mourn it, Voyager 1 will be in the safest place any human artifact has ever been, at the beginning of the longest and least eventful part of its existence. Everything we have measured tonight, every countdown clock, every fading ration, every clogging line, all of it governed the mission. None of it governs the machine. The mission dies in the 2030s. The machine does not. And I can now tell you that the question this video asked in its first 3 minutes, how long can our spacecraft survive in space, splits permanently in half on that morning. Survive as a working, speaking, thinking machine, a handful of decades, and we have now walked every clock that enforces it. Survive as an object, as a thing our species made, out there, intact. That is a different question. The answer does not come in decades, and it does not come in centuries, and it is time to pay the debt I took out at the top of this video. The number I owe you, the absurd one, the one with a map of the future Earth bolted to it, starts with a grapefruit-sized sphere of aluminum passing over your house tonight, and it ends 1 billion years from now. Let's count what outlasts us. Sometime tonight, weather permitting, a piece of the Eisenhower administration will pass over your house. It is a polished aluminum sphere, about 6 inches across, a little over 3 pounds, roughly the size and heft of a grapefruit, and it went up on March 17th, 1958. Its name is Vanguard 1, and it was only the 4th satellite our species ever placed in orbit. Think about the world it left. No human being had flown in space. The interstate highway system was 3 years old. Every other object launched in that first frantic year of the space age is long gone. Sputnik burned up within months. The early companions fell one by one, dragged down by the thin fringe of atmosphere. Vanguard 1 got lucky. Its orbit swings high, far above the drag, and so while its siblings rained down as meteors decades ago, the little grapefruit just kept circling. Its radio fell silent in 1964. Run the scorecard and be honest about it. Level 2, gone for over 60 years. Levels 3, 4, and 5, gone with it. By every standard this video opened with, Vanguard 1 has been dead since Lyndon Johnson was president, and Level 1 has not aged a day. The sphere is intact. The solar cells still cling to its skin. The little antennas still jut out at their 1950s angles, and the current projections say it stays up there for another couple of centuries, into the 23rd century, the oldest human object in space, outliving every person who built it. every person who mourned its silence, and every person watching this video. When it finally comes down, the United States Constitution will be more than 500 years old. And here is the sentence that this whole final act turns on. By the clocks that govern dead spacecraft, Vanguard 1 is a short timer, because once a machine stops trying to live, once there are no watts to ration and no poses to hold, the only clocks left are orbital mechanics and erosion. And in most of space, both of those clocks tick in geologic time. The graveyard orbit from Chapter 15, that parking lot of retired satellites above the working world, sits in a place with no drag at all, and the dead fleet parked there will still be circling in millions of years. Not a poetic millions, a literal, calculable millions, which brings me to the strangest spacecraft in this entire video, and to the debt I have owed you since the first 3 minutes. In May of 1976, NASA launched a satellite called Lagios, and I need you to picture it, because it looks like nothing else we have ever flown. It is a cannonball, a brass and aluminum sphere 2 feet across, weighing about 900 pounds. Its entire surface studded with 426 small glass reflectors, so that the whole thing resembles an enormous, extremely serious disco ball. And here is its parts list. No solar panels, no battery, no computer, no radio, no thrusters, no fuel, no moving parts of any kind. Lagios carries none of the machinery this entire video has been about, which means it carries none of the countdown clocks. It cannot lose power, because it never had power. It cannot lose control, because it never steered. It cannot fall silent, because it never spoke. Every death you have watched tonight is impossible for this object, because everything that dies was left off the drawing. So what good is a cannonball? This is my favourite part. Scientists on the ground fire laser pulses at it, and those 426 reflectors have a special geometry that bounces every beam straight back the way it came. Time the round trip of the laser, and you know the distance to the satellite within a fraction of an inch. And from thousands of such measurements, made from stations all over the planet, geologists can watch the continents themselves move. Lagios is the fixed benchmark in the sky against which we measure the drift of the ground under our feet, the slow ride of the plates, an inch or so a year, the speed your fingernails grow. Run the scorecard on that and enjoy how backwards it is. Levels 2, 3, and 4 never existed on this machine. And Level 5, science, is alive and thriving after 50 years, with no sign of ever stopping. It is the only spacecraft in this video that skipped being alive and went straight to being useful forever, and its orbit was chosen to match. Lagios circles 3,700 miles up, far beyond the last wisp of atmosphere, in a groove so high and so clean that the calculations give it a lifespan of 8.4 million years. Now sit with what that number did to the people who launched it, because they saw the problem immediately, and the problem had never existed before in human history. This object will outlast the shape of the world. 8.4 million years from now, when gravity finally reels the cannonball back in, the continents it spent its career measuring will have moved. The coastlines will be wrong. The maps will all be wrong. Whoever, or whatever, is here to see it come down will be looking at a relic from a planet that no longer looks like this one. So NASA did the thing I promised you in the opening minutes of this video. They asked a man to draw a map of the future Earth. And the man was Carl Sagan. The plaque he designed rides inside Lagios right now. A small steel sheet engraved with 3 portraits of our planet. The first shows the continents of 268 million years ago, fused into one great landmass. The world as it was before the world we know. The second shows the continents of today, the map on every classroom wall. And the third shows the continents of 8.4 million years from now. The Atlantic wider, the coastlines redrawn, a forecast of the very drift this satellite was launched to measure, with the dates written in binary beside each picture. It is a message addressed to the deep future, a note that says, in effect, this is what home looked like when we sent this, and this is what we calculated home would look like when you found it. The satellite measuring the drift of the continents carries a prediction of where the drift ends up. That is the map. The debt from Chapter 1, paid in full, 8.4 million years. And even that is not the top shelf, because riding out of the solar system right now, bolted to the sides of Voyager 1 and Voyager 2, are two golden phonograph records, copper discs plated in gold, carrying sounds and music and greetings from the Earth of 1977. And where those records are going, the erosion clocks almost stop entirely. Interstellar space has no air, no moisture, no weather, nothing to corrode or dissolve or wear. The only sculptors left out there are the occasional drifting dust grain, striking rarely across centuries, and the slow, patient sandblasting of cosmic rays, picking off atoms one at a time. Engineers and scientists have run those erosion rates seriously. And the serious answer is that the engraved information on those records should remain readable for more than 1 billion years. Anchor that number, because it refuses to fit in a human head any other way. 1 billion years from now, the sun will have grown hotter, and the best projections say Earth's oceans will be gone, boiled away. The planet transformed beyond recognition. The two golden records will outlast the oceans they recorded. The sound of surf, pressed into gold in 1977, is on track to exist longer than surf itself. The machines carrying those records will be silent by the early 2030s. And then, intact and unhurried, they will simply continue, at 38,000 miles per hour, through a neighbourhood with nothing in it to stop them. And they do have an appointment. In about 40,000 years, Voyager 1 will drift past a small red star called Gliese 445, passing within less than 2 light-years of it. The first close approach our species' hardware will ever make to another star. Every person who knew about the appointment will be 40,000 years gone. The spacecraft will make it anyway. It will arrive on time. It has never once been late. That is the answer to the second half of our question. The half that opened up on the last morning in Pasadena. So now, finally, we can put the two halves together, lay every number from tonight on one table, and answer the question on the title of this video, completely, in plain English. How long can our spacecraft survive in space? You have earned the real answer now, and the real answer comes in 4 shelves, and you have met every machine on every shelf. The first shelf is measured in minutes. This is where the unlucky ones live, the spacecraft that never survived their first day, killed by the shaking or the sound or the punch of separation, or by that one hinge that swings 99% of the way and stops. Chapter 4. The 8 minutes of violence and the fold that follows. A meaningful fraction of everything we have ever launched died here. Machines built for decades, finished before their builders got home from the launch party. The second shelf is measured in years. This is the workforce, the ordinary satellites in low orbit, living in the shooting gallery, riding the oven and freezer 16 times a day, sanded by atomic oxygen, dodging tracked debris and absorbing the rest. A small CubeSat might last months. A typical working satellite gives 5, 10, 15 years of service before the fatigue and the fading panels and the emptying tank close the books. Most of the machines humanity has ever flown lived and died on this shelf. The third shelf is measured in decades, and this is the shelf tonight has mostly lived on. The shelf of the well-built, the well-crewed, and the lucky opportunity, warranted for 90 days, gone at 15 years. Cassini. 20 years from launch to its last transmitted breath. The space station, roughly 32 years old when it takes its final dive around 2030. Hubble, past 35 years and still working, limping on purpose. And Voyager 1, closing on 50. The record holder, the outer edge of the shelf. Notice what every machine on this shelf needed to get here. Power still flowing, fuel still in the tank, parts still turning, and an Earth still choosing to listen. Decades are not what these machines are capable of. Decades are what those 4 conditions are capable of. And tonight you have watched each of those conditions fail somewhere, by and the 4th shelf is measured in millions and billions of years. Because the longest part of any spacecraft's life is the part after the last signal. Vanguard 1, silent for 60 years. Aloft for 2 centuries more. The Graveyard Fleet, circling for millions of years. Lagios and its map of the future Earth. 8.4 million years. The Golden Records, readable after 1 billion years. Outlasting the oceans. The question this video asked splits in half, and the halves are almost comically unequal. Survive as a mission, and the ceiling is about half a century. Survive as an object, and there may be no ceiling worth naming. Nearly everything we have ever launched will exist, somewhere, long after everyone who remembers launching it. One quick look forward, because the shelves are not fixed. The next generation of spacecraft is being designed to age slower on purpose. Electronics that shrug off the radiation that killed chips in this video. Designs that cut down the small spinning parts, so there are fewer marathon runners to lose. New nuclear power sources with more watts and longer embers. Machines that diagnose their own faults instead of waiting 2 days for Pasadena. And the biggest change is already flying. Because in recent years, for the first time, robotic tugs have docked with aging satellites in orbit and extended their lives. And refueling vehicles are in development now. The one rule this entire video has obeyed, that nobody can ever touch the machine again, is quietly being repealed. Somewhere on a drawing board today is a spacecraft meant to work for 100 years. And after tonight, you know exactly which clocks its designers are fighting. So, end where we started. In Pasadena. In the small cluster of offices where the oldest conversation our species has ever held is still going on. The team still badges in every morning. The ember under the floor of their spacecraft still fades. 4 watts a year. On schedule. The meetings at the kitchen table continue, and the rooms of the old house go dark one at a time, so the last room can stay warm a little longer. Everyone involved knows how this ends, and everyone involved comes to work anyway, and the machine holds its pose. 49 years in, still speaking, still heard. A spacecraft survives not until its metal disappears, but until the first system it cannot live without finally fails. For Voyager 1, that first system fails within the decade. Every other part of it has 1 billion years to go.